Good morning, everybody. I will speak about time-dependent behavior of the Callovo-Oxfordian claystone, and I will come back about what we have learned during the last 20 years. So I will first introduce the subject and speak about the CGO project, which is in France the geological repository for high-level and intermediate-level long-life nuclear waste. We will be in place in Callovo-Oxfordian claystone, and I will speak about time-dependent behavior with characterization performed on sample with many university laboratory from all France, and some are there today. And I will also speak a lot about the observation we perform at the Geothermal underground Recherche laboratory. And after I come back to the technical solution with the compressible material we use for lining in order to take into account this long-term behavior in terms of the design of lining. And I will finish with some conclusion and perspective. So the Andra is a French National Active Waste Management Agency. Is in charge of design and implement a deep geological repository. So this repository, if it is authorized, it's called CGO, is planned in east of the Paris Basin, here, in Callovo-Oxfordian claystone. This is at a depth at around 500 meters. The thickness of the layer is about 130 to 150 in an area without any faults. Here you see a scheme of what could be this geological repository with an access shaft, with an access shaft here for excavation and people. We have also ramp here where the waste package will go down, and we have two main areas. One with for intermediate level waste. This is a tunnel of about 10 meters diameter, 500 meters long. And here this is for high level waste. High level waste, there is they emit heat. So we will place it in the micro tunnels at about 150 meters, and it's micro tunnels of about 80 centimeter diameter with a steel casing in order to place the waste package easily and retrieve it. So there is specificity of this type of project. We have to be reversible for at least 1 century. We will start with a pilot phase. So this is a date we plan now, if it is authorized. So you see that we have a gradual development. And the operation lifetime is about 120 to 150 years. And at the end it will be something like this, depending the decision will be taken by people who are in charge at this time. So it's a very long time life. So long-term behavior is something important for design it. So something about the digging and support methods. We will use different methods. We will use classical conventional methods called CTM for intersection and small drift, but we will use a lot of tunnel boring machine for long galleries, and some. So we will excavate with different things. So one in terms of geomechanics, what is important? So as I said, it is a long operational lifetime. The size, the length, more than 100 kilometers of galleries, and it is underground nuclear facilities. So we need a good understanding of rock and structure interaction in order we have to well characterize the Callovo-Oxfordian thermo-hydromechanical behavior. We have also the structural behavior with the concrete, and it is necessary to take into account consequence of the construction and methods. These have two main outputs. One, it is input for performance assessment and calculation. I will not speak about that today, but it's mainly due to the fact that when you excavate, you create damage, and damage have changed the permeability of the rock in the vicinity of the openings, and this is have impact of long-term safety, because the long-term safety is linked with the low permeability of such material and the thickness of the layer. And I will speak more about design of different elements of the repository. So, since more than 2 decades, Andra has been leading several research programs with the university to perform lab tests on samples to characterize the THM behavior and define parameters, but also to develop models. And we have, from since 2000, we developed a laboratory at 500 meters. It's called the Multiscale Underground Research Laboratories. This is, we developed with the sequential approach. We construct different drifts in order to study and demonstrate technological feasibility, but also to enhance the understanding of the hydromechanical response of the excavated Callovo-Oxfordian and the interaction between structural and support and the surrounding rocks. Of course, data we acquire at this level, it's also used to check validity of models at the real scale, and after we use the model to extrapolate as function of time to define what will be the evolution of the repository. In this case, as I say that it is about a long time-dependent behavior is an issue for the design and optimization of gallery. As you see here, the lab is not you have a parallel gallery in the two main directions due to the fact that we have an anisotropic stress field. We have performed a lot of hydrofracs and also other type of model to determine the in-situ stress state. Here you see at the regional scale, this is where we have the lab, and you see the orientation in the Callovo-Oxfordian. We always find that the fractures are the same direction, meaning that we have an anisotropic stress field. This anisotropic stress field at the main level of the laboratory at 500 meters, we have nearly the vertical load is equal to the horizontal median 1, and we have an anisotropy of a maximum of 1.3. So, if I come back to what we have done on sample, this is many things that we have performed with many laboratories. I will not present all, I just give some example of what we have done. So we perform many creep tests with loading and unloading at different laboratory stress level, different confining pressure. We compare it to triaxial tests. We also perform triaxial tests at different rates. And we also vary under different conditions in terms of relative humidity and temperature. We have to know that it is difficult to perform creep tests due to the low permeability and the low strain level. So we have always questions about initial state of sample, the level of saturation, and pore pressure. It's quite difficult to measure during creep tests. So here it is some example of some results. Here it is a long monoaxial creep test performed at GRS in Germany with multi-stage loading, but also unloading, where you can see that even after unloading we start again to creep. Here it is example of we have performed with different laboratory, different same tests to check if they find the same result, which was the case. And here you see that we perform a loading after a creep test and after we load again. And you see that during at different level from the deviatory stress to the versus the peak stress. And you see when we load after, in fact, we compact the material and the strength increase. So creep rate increase strongly with the deviatory stress level. This is as common. Creep rates increase slightly with confining pressure. This is things we can see in some results here coming from Lille. And the volumetric strain are mainly compressive. We have anisotropy on the response on sample with the bedding planes. Here you see some example of microtomography and DVC analysis on axial deformation field in uniaxial creep test. Here you see the bedding is oriented at 45 degrees, here at 90 degrees, and you see that the field is not homogeneous. I think you will come back on that after, Jacques. So, of course, at a small scale, we see there is difference, and we see that bedding planes play a role in the creep response of the rock. So we also have been interested in something which is a creep threshold. So this is example that test has been performed at LMS. They perform the test in a mine nearby Nancy. Why in a mine? To have a constant temperatures and relative humidity. Here you have just the relative humidity, but the temperatures nearly don't change except when you go in and you move it. So we don't see what we have seen. It's just some example of result into orientation that we always observe creep, even at low deviatory stress. So this is something which means that with the absence of measurable threshold creep at the laboratory is not fully convenient with an anisotropic natural stress state in situ. So it's also a problem for modeling. So it means that as we have an anisotropic stress field, if you have no creep models with a threshold, it's very difficult to make calculation. So if we now I jump to what we have seen in situ at the Laboratoire de Mécanique Recherche Laboratory. Here, just to know that we have tested, as I show in CGO, we will use different methods. We have used different methods in terms of excavation with pneumatic hammer, rod header, and also in terms of support. And here you see we also go to TBM. This is not a full face TBM. We are not able to handle the rod in the lab, which is due to the size of our shaft, but we use a TBM. So what we do also is we start from low support drift to steep support. The idea was to see with the low support what is the convergence of the rock. And the convergence is linked with the different behavior, mainly creep, but other things. You have also hydromechanical coupling at the beginning and things like that. And after, of course, in the repository, we will have tunnels with the steep support of concrete. And what we want to understand, this is how convergence loads the concrete lining in order to design it. So one of the things, I will not go in detail, it is most of you know that when we, due to the strength of the rock, it is about 21 MPa of uniaxial compressive strength. We are at about 500 meters deep, so the strength of the rock is not sufficient. When we excavate, we have a significant excavation-induced fracture network which appears. It's form of shear and tensile fractures. Tip of fractures are similar, but the extent depends on the drift orientation. Here you see, for example, we perform a lot of boreholes. All the boreholes we perform at the lab are core, and we are able to analyze type of fractures and orientation and density of fractures. And from those data, and also from front data, we are able to define models for the two direction and the extension. So the extension of shear fractures is larger than tensile fractures, and the extent is not dependent of the excavation method, but it is dependent of the time of the support emplacement. As long as the emplacement of the support, you increase the extent of the damager. So I will not go into details, but it is to show you that we perform different type of support with loose primary support in conventional tunneling methods. Here it is sliding arches with a rod bolt. Here it is a shotcrete, and here you see that we have a wedge with a perfect elastoplastic behavior. And this type of drift is used to check and analyze the convergence of the drift. After, we also check, here it is a stiffer primary support lining with 45 centimeters of shotcrete. And after, we excavate, for example, like this, and after we cast in place some lining. Here it's a lining about 30 centimeter thickness. One of the things we also do a lot, it is we have changed the diameter of the excavation from nearly, for drift, for 4 meters to nearly 10 meters, and we show that there is nearly no scale effect. The behavior is nearly the same. We have also micro tunnels at 0.8 meters, who also show the same type of fluctuation and the same behavior. So if I go on convergence evolution, I just give here two examples. On two drift, one oriented here along the major horizontal stress, and you see here that the horizontal convergence is larger than the vertical one, and you see at a long time that the rate is nearly similar. You also can see what is the extension of the fracture zone, and you see that the larger displacement are observed where we have the larger fracture zone. On the other direction, here we have an anisotropic stress field with a major stress horizontal. We have large plastic deformation here and fractures, and you see here that in this case the vertical convergence is larger than the horizontal one, and you also see that the rate are not the same, and the decrease of the rate is in the vertical direction. The decrease is more slow. For all this type of convergence, we have used the semi-empirical law developed by Jean Sullen. It is published in the work from Guyacan and Carrillo, and we show that we are able to reproduce and to predict the convergence of such support with this empiric law, showing that we have a part due to excavation, the advancement of the front, and another part due to time. These things all show that the rate decreases as function of time, but we don't be really stabilized. We continue to have deformation. If we go a little deeper to try to understand what are these long-term behavior or what's happened, here I show some result. Here you see we have excavated this drift, but previously we have from another drift an extensometer here, which is this one, which is in fact measures the radial displacement of this new drift. This is the step of excavation as function of time, you see that before that we reach the section, we already see some displacement, radial displacement, and after when we cross the section, we have a large displacement. And the displacement are more important at the wall than in the far field, which is really classical. From that, we try to analyze what we call the pseudo-intermediate displacement. It means that it is the displacement we are able to measure during excavation, just when we excavate. And what is remaining, because when you excavate, and after you support. So the time of excavation is short compared to the time of support in the CTM methods. So you see that with that we have what is more elastoplastic displacement and what is more different displacement. Here there is link with hydromechanical coupling, but there is also some creep effect. You see that at 90 days, elastoplastic deformation represents nearly 40% of the deformation, but at 900 days, it's less than 30%. So you also see that further deep in the rock, different deformation is very small. The contribution of far field is about 5% of the total elastoplastic deformation and 4% of the different deformation. And when you go further in time, it's decreased. So it means that most of the long-term deformation we observe for convergence are nearby the tunnel, where you have the most important deviatory stress field, and in the fracture zone. I don't show here, but we are also able to show that the rates are also linked with the density of fracture we have in the fracture zone. So, if I jump to the other techniques with the TBM, we use this type of TBM. So, what is the difference? So, you in place segments, who are precast segments. Of course, with this method, you need to fill the void between the segment and the rock. We have convergence, but they are not enough, as with soil, to fill the gap. So we have to fill the gap with materials. It is necessary with the TBM because if you don't do it, after it is unstable and you have some problem of adjustment of different rings of segments. Just to show what is so this is the curve I just present with the CTM, with the short quit and compressible wedge at the same scale, and here you see in the same direction, the TBM we use, you see the deformation are larger. Why the deformation are larger? Due to the fact that there is no support over the shield. And in our case, also the filling of the void, it's about 2 diameter of the front. So it means that there is no support, so you let short-term convergence larger, but after all, the behavior is nearly similar. Here, due to the fact that you have a very stiff support, you see that convergence stop at the wall, which is due to the boundary condition, but you can have some compression in the fracture zone due to the fact that we have open fractures, and due to the long-term behavior, you can have some closure of some of the fractures. What is important, so if you have a stiff support, you have the rock who converge on it, and what it happen, it will apply stress on the lining. Here you see, this is not stress, this is strain, because it's more easy to measure strain in lining. And you see that when we in place the segment, just when we start to load the segment. And here you see from over nearly 10 years that we continue to load the lining. I show that we have anisotropic convergence. So meaning that in this direction we have larger convergence horizontal to the vertical one. And you see here, if we check, we have rings where we have measurement in all the rings. And we see that if we check intrado and extrado, strain or stress, it is the same because it is nearly elastic at this stage. You see that you have a sinusoidal curve and in opposition between the intrado and extrado, meaning you have an anisotropic loading of the line, which is important to take into account for design. So you see that we have evidence of convergence, and after we have to go to make a design for tunnels with a long life. Here it is data from convergence on the same gallery I present. Here it is extrapolation to 100 years, just to show, with the semi-empirical models, but also with other models like elasto-viscoplastic models or things like this. You see, even from that we have a huge range, but you see from 20 years to we are there to 100 years or more, you will have convergence, you will have load on the line. So, even if the convergence rate decreases with time, and they are slow and small, that will conduct to a significant convergence and a loading of the lining over this period. And the main idea we have, it was to try to damp the convergence to reduce stress increase in the lining. For that, we want to use compressible material. Compressible material is a material, you see here is behavior in odonometric loading. You have a small elastic part, and after you have a plastic deformation. If it is purely plastic, it is better, but it's hard to find such material. And after, at such, so we need a plateau as large as possible in order to damp the convergence. If you make some calculation about tunnels, here you see evolution of the maximal orthoradial stress in the lining it's a concrete say 60, 70. You see that, and after we increase, we apply this this layer of compressible material, and you see at the beginning with this calculation with no layer, we will have a maximal stress over 60, and after when you put some compressible material, you see that you decrease the stress level, and this is what we are interested in. After some time, it's not necessary to increase more because the length of the plateau is enough to damp the convergence we will have over the operation life of the tunnel. So we want to check if it is possible and if we found in situ the same result. So here you see that, as I said, from this in this drift, we have to fill the void between the segment and the rock. Here in this section we use a classical mortar. In this one we use a compressible mortar with polystyrene balls, which has the behavior I showed you before. And here you see total stress measurement, and you see that in the area with the compressible material, the stress are nearly divided by Q. This is also seen in the term of when you check with orientation. It's not avoid all the anisotropic loading, but it decreases the amplitude of the stress transfer to the lining structures. This is interesting, but one of the difficulty in such with such things, it is that after, when you inject, it's difficult to know what is exactly the thickness of the material you have. So it's difficult to know what is the damping effect that you can have with this type of material. So that's why we develop what we call the VMC lining. So it's a classical line, and here you see that you have a layer with a compressible material. Here it is one type of material. This is a small shield. It's ceramic made with a Callovo-Oxfordian claystone. We assemble with some work, and we have a huge program on this material, but on other material, to characterize at different scale the material. And to try, for example, to make some, so you start like this, and after you see that at the end you have a plateau or a palier about 40%. And we test that, we develop models to represent this type of thing, but we have also to demonstrate that it is technologically feasible, so we are able to construct, to move it, and also to in place in a TBM. This is what we have done here, and we have excavated in the drift. This is a drift. Here you see the layer with a compressible segment. Here you see. So we are able to show that we demonstrate that the fabrication, handling, and emplacement of this type of compressible segment is feasible, and it has no impact on the TBM advancement. And we also show here that the compressible layer, which is the result here, we have less stress in the concrete compared to the one with classical mortar, and also with mortar with polystyrene boards. So, last 2 decades, Andra tried to characterize time-dependent behavior of Callovo-Oxfordian claystone in order to design CGO underground structures. At laboratory, we show that we have creep. Creep remains challenging for such claystone. There is evidence of creep with increasing rates with deviatory stress. At this stage, we have no really evidence of creep threshold. And when we go at the lab, we show that over nearly 20 years, drift continue to converge with decreasing rates. So, and when we have a stiff support, you will have increase of the load in the support. This is what we want to do. So, in order to handle this time-dependent behavior and also uncertainties on this behavior, we propose to use compressible element to dampen and delay the effect of the Callovo-Oxfordian claystone convergence to reduce stress transfer on concrete structures, and we propose it to use it in the design. We have a solid feedback on technical feasibility and also on behavior on compressible support and lining. Gallery scale experiment confirms that these solutions are effective in reduction stress transfer in the lining. This technical solution not really increase the robustness of the design process, but also offer technical and economical benefits by reducing the thickness of concrete lining. Of course, a better understanding of time-dependent behavior will also help to optimize design and value. So thank you for your attention. I have to acknowledge all my other people working with me at Andra, some are there in the room, and also all the colleagues from different universities who work a lot on this type of programs. And a special thought to Pierre, who, for the all interesting discussion about the time-dependent behavior of the Callovo-Oxfordian claystone and the challenging question we have to try to answer when he was at the Commission Nationale d'Évaluation.
Thank you very much, Gilles. Presentation, comprehensive from all perspectives. Question, please.
Thank you, Gilles presentation. I have a question about the creep threshold. You say that has not been laboratory observed, measured, and I have an idea with I think the first time it was presented to me was by Pierre. So the idea is that the in situ stresses are anisotropic, and so you have natural deviatoric stress, and if you can admit that the creep threshold is at least equal to this natural deviatoric stress.
This is what we do implicitly in the modeling, because if you don't use a creep threshold, it's really difficult to perform models with long-term behavior, because everything is moving, so you have no boundary condition. So in fact, when we make models, we use that. But, and it was also a question from Pierre, are you sure that it is a good one and that we don't have to model in another way? So we tried with Alexandre and a team from LLS to try to find, but also other tests with in other laboratories like GRS with very small. Most of the time you have some creep, some deformation. After, it's always the same problem with sample. That the sample, as we have to take it from the lab and go up, and we release the stress, and it is always, you have risk of damage. We try to avoid it with microtomography to check, but you also, due to the unloading, decrease the saturation, you have some evaporation. So it's difficult, it's remained a question, not only for the creep, but also for understanding why the stress state is like this, which is not, at this time, scientifically demonstrated. We have a huge confidence of the stress state because we have many measurements, and it is linked with the direction, it's linked with the uplift of the Alps. So but the evolution of the stress state as function of time from this time is not fully defined. We try to find people who are interested in this subject which is a really scientific problem. In our opinion, for us, it's not a huge problem because the knowledge of the stress state is really robust. We can have questions about if we are not able to explain why the stress state is like this. Are we sure that we are well known how the stress state will evolve as function of time? So that's why, even if we have a robust design, we will continue to work on this stress state, but also to better understand this creep, deformation, and sequences. Ready?
Thank you, Gilles. Regarding, creep behavior, I think that yesterday we had a very nice presentation of creep spiders, showing that the creep in salt, the mechanisms involved are fully explained. This is not the case of this material. It's not always full of clay, but also the carbonates, the quartz, and the other, for which the micromechanisms are not very clear. One can think that maybe the unloaded samples taken from in situ going to the laboratory, even if attention had been paid to do as best as possible, we cannot distinguish easily the initial consolidation, creep, and maybe the sample is not fully saturated, and the constant times are various related to hydrolyte, related to creep, the others. So I think that there are very convincing results which have been obtained in situ, showing that there are some initial anisotropic stress in the time scale, geological time scale, the relaxation has not been produced. Therefore, it is obviously clearly there is a threshold, and if in the laboratory we did not observe that, there is something wrong with the laboratory, not in the field.
You're perhaps right, but it's always difficult to convince people for such result. But
yeah, it's complicated, of course. I agree. It's very complicated too. Yeah, very good tests have been performed in the laboratory, but it is so complicated.
One of the things which start to be encouraging, as many micro tomography is used and used more. Now we start to make some quick tests on such at such level, who will help to see that the strain fields are not homogeneous, and better understand perhaps the effect of beddings, heterogeneities, and things like this. So perhaps we will more understand the micromechanics. It's not truly the case now, but I think that in the following, I don't know the number of years, but we will have better results.
Jean?
Thank you, Gilles, for the nice presentation. I have a question about this natural state of stress with the anisotropy. As you mentioned, it's commonly admitted that it's due to the uplift of the Alps, but I know that it's been controversial, and for example, François Cornet had different ideas about it, more related to hydromechanical effects, consolidation, and what is, I would say, the up-to-date opinion about the origin of this anisotropy?
So the orientation is linked with the orientation given by the uplift of the Alp. But the problem is that the uplift of the Alp nearly stop, and so it means that you have not a lot of when you have a GPS on the sedimentary basin of Paris, you don't see velocities at the top. The other thing it is that you have a layer of salt. So if you have a layer of salt and you push, you have a decoupling between the top of the layer and the salt itself, due to the salt. So from that, we are not able to explain why now it remains this type of anisotropic stress field. One of the ideas, we work a lot with François. One of the ideas was also linked with you have huge different stresses between the claystone and the sandstone. Here you see. Here this is the Callovo-Oxfordian, and here after you see that you have not the same. You have the major one and the minor one is here, and the top here. So one of the ideas of François, what it is that it remain very small deformation of the Oxfordian and Dogger limestone, with the links with the initial fracture due to the uplift of the Alp, with a dissolution pressurization effect that where you could have some displacement here, which something like a sharing of the claystone layer, who could explain such type of profile of stress. When you put number on that, it means that it is possible, that it works, It will also explain something I don't speak about, but we have also some overpressure at the middle of the layer in terms of pore pressure. But at this time, it is not more demonstrated. So that's why it's also, this is one of the possible way to explain it, but it's remain calculation and more things about that.
So my name is Jaques DESRUES. I will tell you about multiscale modeling for underground opening, storage, and waste disposal in rocks. And the subtitle, thank you, Alexandre. The subtitle is a kind of a declaration: multiscale FEM, DEM, and FEM square methods allow to undertake both the complexity and the variability of rock behavior. Okay, so this work has been performed in Laboratoire de Mécanique in Grenoble, and I have to acknowledge the contribution of a lot of people who have been working on this topic together with me in the past years, and my presentation will try to be still up to date with respect to the development. So this is the outline. First, I will talk of the motivation for multiscale modeling. Then, how does it work, and how does it perform? Then I will specialize the topic on the Callovo-Oxfordian material. I will speak about taking into account the variability of the material, spatial variability of the material, and then conclusions. Okay, so motivation. So safety assessment and design and in underground opening, storage, and waste disposal requires proper modeling tools to catch the essential feature of deformation and failure in hardware or software works. The point is what essential features do we need to incorporate in the modeling tool. Deformation processes around boreholes, carrying and excavation often, if not always, involve more or less distributed localized failures, as has been shown in the previous presentation by Gilles ARMAND. With this nice exploration of the localized, distributed localized failures around galleries. Localized failure is observed also at a very small scale. For example, in a Pierre-Bézel triaxial experiment under high-resolution microtomography at the SRF in Grenoble, on a specimen 1 millimeter in diameter Callovo-Oxfordian specimens, we see that we have a localized fracture here in the specimen. So several scales are involved in the overall deformation process. This is an evidence of observation. So, how to deal with several scales in modeling? Homogenization is it's a long time that people have been developing methods for homogenizing the behavior of materials. But there is a method which is more or less a newcomer since 2 decades, probably now. It's multiscale modeling. So several scales, okay, but also we have another problem, which is variability. At small scale, rocks are essentially heterogeneous materials, different constituents with different mechanical properties of the constituents. So this multiscale modeling allows to take this into account. Much more easy. It's much more easy to take this into account with the multiscale modeling than by specifying a large-scale constitutive equation. On the other hand, rock masses often show variability in terms of morphology, mineralogy, consequently mechanical, hydraulic, and other physical properties. So variability is observed at different scales, and at all these scales, the variability can be either randomly distributed, like for example here in the Callovo-Oxfordian argillite, a long thin section. We see that the distribution of the different constituents is not the same here and here and here. So this variability is something which is constituting the material itself. So we have to take into account the variability at this scale that I will call mesoscale, with respect to this which I will call micro. Okay, but variability can be also geometrically organized, like for example here in a vault sandstone at the centimetric scale, you see, and the millimetric scale here. So variability is something that we will be able to take into account using multiscale approach. So the keyword in the second will be multiscale modeling and variability. So multiscale modeling. So what is it and how does it work? This is what I will try to explain. So multiscale FEM and FE2 methods are concurrent multiscale analysis. It consists in the association in a single modeling process of two sets of numerical analysis working simultaneously. So it means running at the same time at two different scales. So one numerical analysis is at the macro level is an FEM model, and then several numerical analyses are working at the micro scale. It can be discrete element method or finite element method. So this is working simultaneously. I will explain how. And it's also called integrated or hierarchical. So using such a multiscale approach allows to derive quite naturally the behavior of the rock from its components and the way they interact within the microstructure, and including progressive degradation of the microassembly under mechanical and multi-physical loading. But also it allows to take into account at no additional cost the variability of the material, whether random or organized. So the work since the end of the years 1990s by a large number of renowned authors in the international community, not especially in geomaterials, but in the material science field. So multiscale modeling, how does it work? So I will show in the case of FEM and FEM square, FEMDM and FEM square. So in concurrent multiscale analysis, a set of concurrent numerical processes are run simultaneously. I already said that. One process at the large scale and one virtually large number of processes modeling BVPs at the small scale, each small scale process being associated with a specific region in the large scale model. So different methods, okay, so FEMDM here and FEM square here. In the FEMDM we are using discrete element method at the low scale, and in the FEM square it's again finite element method at the small scale. So okay, so this is the method. So we have a structure, and this structure is modeled using finite element method. In each element we have several gauge points, several integration points where we need to know the constitutive equation. That in the usual FEM approach, we write a constitutive equation, mathematically described, and this equation, passing the deformation gradient to the equation, gives back the stress tensor and the consistent tangent operator that we need for the Newton-Raphson iterations. The idea here is to change, to use a new constitutive modeling concept, which is a numerically homogenized law, relying, for example, on discrete element method or finite element method at the low scale. So you see, we have such process associated with every gauge point in the macro structure. Okay, what do we need to perform this kind of computation? We need a FEM, in the FEM-DEM case, we need a FEM code and a DEM code, plus a bridging procedure. In the FEM square case, 2 finite element codes, which can be the same or not. So in our cases, we use the FEM code Lagamine from Liège University. It was also implemented using flagship. At the micro scale, we use in-house DEM code. For the FEM scale, FEM square, we use flagship for the small scale. And the bridge, the principle of the bridge is to incorporate directly in the finite element code, in the macro finite element code, to incorporate directly the DEM code or the FEM code related to the small scale. So it's we are not exporting using an extra constitutive equation. This is running at the same time during the process, during the modeling process. So how does it perform? What do we get as a result using this method? The biaxial. So I will show the biaxial response, shear band emergence, excavation modeling. Let's illustrate first using the FEM-DEM method. Elementary biaxial response. I will show the local response, that's to say, using pure DEM computation. So this is the constitutive law at the level of the contacts between grains. I will not insist. This is the result that we get. You see, it's rather noisy. It's because we use a limited number of grains. Otherwise, it would be too much computing time. Still, we have checked that this response will provide a proper response integrated at the level of the macro scale. So this is the response that we get. So now let's go to the double scale biaxial response, and we will see that we get the emergence of the localization. So this is the biaxial case, and this is the response that we get. We have here a recall of the pure DEM response, and this is the response of the double scale method. So it's completely different. So what happens? What happens is the reality of the world. We have localization. We have localization because we have concentration of this behavior in a localized part of the specimen, and this is the deformed structure that we get, and you see that inside the shear band, this is the structure. So the green means that the cohesive part of the contact law has been destroyed. So this is completely destructive with respect to cohesion, while outside we have still the cohesion working available. So so we are able to model a localization. In the case of the excavation problem, where this is a typical modeling of an excavation, This is a borehole, a picture of a borehole deformation. We see this spiral localized deformation, and what we get using our constitutive double scale model is we get this, which is reasonably well fitting the field observations. Okay, this is nice, but we have the mesh dependency. This is very classical. It's a well-known issue, and mesh dependency means that if you change the mesh, you change the result. And this can be mitigated using second gradient regularization. I will not enter into the details, but the idea is that the double scale, the small scale model will give the first gradient part of the considered equation, and we add the second gradient part to complement the constitutive description of the material, and this will regularize the mesh dependency. I don't explain too much, but I will. Okay, we have constitution in two distinct parts. The first one is coming from the small scale, and another one is specified as simple as possible for the second gradient. Okay, I can answer two questions if you need explanations. So this is very effective. As you see here, we have two different meshes, and we obtain exactly the same shear band thickness. And another example is that with the same mesh, if we change the parameter of the if we have the second gradient, yes, here we see that we change the thickness of the band while the mesh is the same. So the second gradient really controls the thickness of the shear band. Okay, it works as well in the case of excavation. We have different meshes, and we have a thinner description, but in both cases the second gradient regularizes. So what have we learned? Double scale concurrent numerical analysis is an effective modeling option for modeling materials with regard to their microstructure. Macroscale strength of tuning comes out directly from the small scale. From the small scale elementary degradation mechanism, so we treat the degradation mechanisms at the small scale, where we have some good physical assumption which can be posed better than having a black box of constitutive equation as usually. Strain localization at the macro scale results from material strength of tuning. Mesh dependency can be mitigated using second gradient regularization, as easily as with classical constitutive equations. Okay, now what about the Cox case? So modeling Callovo-Oxfordian argillite using, in that case, I will use finite element square. So since the session is devoted to nuclear waste disposal, I wanted to show you what we can do for the Cox. So the problematic has been explained by Gilles ARMAND. So we have I don't explain again. So the question is, what is required to properly model the problem of this excavation, which induces significant localized failure around the galleries? What is required? We need a model to simulate engineering boundary problems, not only academic problems, able to predict failure and strain localization, reflecting the most significant properties of the Callovo-Oxfordian microstructure. Taking into account multi-physical coupling, hydromechanical, thermo-hydromechanical, this is not that difficult to introduce at the small scale. Taking into account experimental observation of the microscale deformation modes, microcracking and inter and intragranular microcracking, debonding, and so, taking into account the dependence of the permeability on the deformation. So all this can be done using the FEM square method. So in this method, we have a hierarchical approach by computational organization, coupling at the macro scale, so the hydromechanical coupling, thank you, will be, the thermo-hydromechanical coupling will be treated at the micro scale and upscaled to the macro scale directly. And we need a second gradient regularization. So this is the macro scale. We will transmit to the micro. We will transmit the deformation gradient, the gradient of the pore pressure, the average pore pressure over the REV, the gradient of the temperature, the average temperature. All this information has to be transmitted to the small scale. The small scale, so the modeling at the small scale is performed. We get back the response in terms of stress, stress state, and the other dual quantities of the input, and also the tangents, the consistent tangent operators. We give this back to the material point in the element, and then we add the second gradient, and this is the model that we use. So now we have to define the microstructure. You see, we have a microstructure that we will model using finite element method at the small scale. So we need a scheme to define representative numerical microstructures inspired by Cox images. I'm not saying that we will, I will explain that. I use the idea of inspiration rather than mimicking, because if you want to mimic, then you don't extract essential features. You make some image, and that's it. It's a local image. It's better. It's necessary to be more conceptual. So the idea is, you see, this is Callovo-Oxfordian. It's a pretty complex picture, isn't it? We will extract. We will not extract this, but we will identify that the fact that there are a clay matrix and some particles that we will extract, and with this we'll define a representative elementary volume, and this volume we will model in finite elements at the small scale. So the clay matrix is discretized in several elements, several finite elements, and the other constituents are modelized as well, discretized as well, and we have interfaces between the different grains. And the interfaces will control both the essential deformation process, because the grains itself are not much deformable. The interfaces are more deformable, and the interfaces will also control the hydromechanical coupling. So how do we generate? We have built tools to generate microstructure. So we have a random seeding, a Voronoi tessellation, then an adaptation of the tessellation in order to check convexity of the grain and different features that we need. And then this is the micromechanical coupling. I will not spend too much time in this, but it's important to say that the grains are linear elastic solids. The plastic deformation will be concentrated in the interfaces, which are cohesive, low, damageable. So the damage is represented here. We have an elastic behavior at first, and then after some deformation, we have degradation of the normal and tangency properties of the interface, and then on unloading, we are back on the elastic behavior, and then again we may enter into the plastic edging. For the fluid flow, it will be relocated in the interfaces. The opening of the interface will control the permeability of the local permeability of the interface, local in the small scale, I mean. So the different interfaces will become more, we will get the different permeabilities. So the fluid forces will be given back to the mechanical part. And it's the same for the temperature. I will not go into more details. Then let's see some examples. So example one, the axial test with hydromechanical coupling. So we have here the microstructure that we use, and as I will explain, this microstructure is the simplest case. We consider that all the grains have the same properties. So it's a mineralogy. In terms of mineralogy, it's homogeneous, the small case, in that modeling. So what do we get? We get localization. The picture that are shown here are taken at 1% axial strain. We see that it's somewhat after the peak of the stress strain curve. But it's in the place where the flow, where the pressure, which was dropping, starts increasing. And then, so here we have the picture of the microstructure at different points. Here, in the middle, in the shear band, we have some degraded interfaces. Outside the shear band, it's not degraded at all. And in the very, very deformed places, the degradation is total, which means that we have no more cohesion in the interfaces. And for the fluid flow, we see that it's a drain. I forgot to say that it's a drain test. We are modeling a drain test, so we see that the water is flowing from the top and bottom of the specimen toward the shear band, which is dilated, and this is reflected by the pore pressure, which is equal to the imposed pore pressure near the draining boundaries, and quite different in the constitutive, in the shear band. Okay, another outcome is the anisotropy sensitivity. If we rotate the small scale, the IV, and compute again with the rotated IV, we will get different responses, as you see here. And this is mimicking quite well what the experiments show in terms of exploration of the effector anisotropy and the mechanical response of specimens. We have, if the material is anisotropic, this layer is anisotropic because we constructed it isotropically and then geometrically compacted in order to get an anisotropy of the IV. So you see that this is a classical observation, experimental observation, and it's well represented. In the case of gallery excavation, still with this small scale homogeneous material. We get if the loading is that way, we are at the this is modeling the progressive excavation of a tunnel. So we have here the pore pressure drop when the front reaches the place we are modeling, and here we have the pressure, the mechanical pressure on the wall, which is decreasing progressively as the front approaches. So this is the loading. So what do we get? We get strain localization, as you see here. This is illustrated here, but it's interesting also to notice that depending on the small scale REV that we take, in this case we have prepared different REVs to see the effect, and we see that this has a real effect on the localization which is predicted, and this is because an REV, any REV built that way has a small anisotropy, inherent anisotropy, because you cannot prepare ideally isotropic REV. This is impossible. So you get a small anisotropy, which will make the specimen, the local behavior to be a little bit that way or that way, and this it's very slight, but still it has an effect on as we see here, it has an effect on the prediction of localization. Okay, so anisotropy, sensitivity, and fluid flow. So here, well, I think I will not comment too much, but you see that we model properly the fluid flow. Okay, so next step, taking into account variability. Have you seen? As I said, we used up to now in this presentation mineralogically homogeneous material at the small scale. But improving the approach is taking into account the variability. So we do not want to be using that simple scheme. Using this simple scheme, we get strain localization, isotropy, fluid flow, that's fair enough, but is the microstructure representation adopted sufficiently realistic? This is not clear, and in fact, as I said, we have this, if all the material, if we do not take into account the small scale variability, the behavior that we predict at the large scale will reflect the small detail which is common to all the REVs, and this is not correct because the material is variable. Okay, so taking into account variability, first we have to take into account the heterogeneity of the mineralogical components. This is the first step, and this. So here we are using we have quartz and carbonate, pyrite and clay. We have some proportions, and so if we use this, if we prepare REVs that way with a large number of grains, reflecting some proportions of the different constituents, then we can prepare different realistic procedure, microstructure. Sorry. As I illustrated here with 250 grains, 500 grains, all of them are 60% clay, 32% clay. We can deal with these different things. Okay, So this is a local integration of the improved microscale behavior. We see that we have a reasonably good response. It's interesting to notice that from 3%, between 2% and 3% of strain, so it's here at the peak. We have the destruction, the damaging of the microscale, but of the IV, but it's starting from here, from the very beginning, in fact. Okay, it's starting. If we go into the very detail, we can see that it's already in this part. We have already the degradation, and this is responsible for the change in the tangent of the curve. So the effect of confining pressure is properly represented, even with comparison to experiments here. And then the strain localization is properly represented as well. I will go to the next part. But okay, we have that's better, but still there is something more, which the evidence of variability of the microstructure itself. I mean, is this representative of this? This is about 60 micrometers, and this is a large thin slice, 3 millimeters, and we see that the IV that we would define from here is not the same that from here and from here. So the idea is how representative is a representative elementary of volume defined using this scheme. In fact, we have a mesoscale variability of the microstructure. Just taking a single shot within a sample is not a proper representation of the microstructure. Variability has to be taken into account. So the idea is to define a way of taking this into account. So we have a collaboration with the University of Poitiers. This statistical analysis have been performed in Poitiers University with selected parameters of each mineral phases, surface, grain size, elongation, grain orientation, hardness, and different parameters. These are representing the histograms of, for example, the local clay fractions. So we see here the histogram. It's for this slice, the local clay fraction is somewhat between 0.4 and 0.6. So the idea, and this is the same for other properties. So the idea is to adapt the IV building tools that I've been presenting before, in order to be able to produce sets of realistic IVs for a given thin slice. We will produce sets of realistic IVs, which means sets of IVs consistent with the observed statistical distributions. So here we see that we have superposed in blue the histogram of IVs prepared using this adapted building tool, and we see that we are able to define a set of IVs which is fitting reasonably well the histogram that have been obtained using the thin slice. It's true for mineralogy, grain elongation, orientation. Okay, so the mesoscale strategy is at the mesoscale. We have a statistical approach to define a set of representative IVs. That's what I have explained. Now, how to use it? So first, exploring the response of the different IVs of a given set. We see here that we have, of course, if we consider a local response of the REVs, we see that we have different responses. Okay, so we have we observe the dispersivity of the response, and it's the effect of the grain arrangement. So we have no strategy to define mesoscale sets of relevant REVs, but what is the next step? The next step is upscaling this to the macro scale. So can we take into account the mesoscale variability at the macro scale? First, let's consider the case of macro homogeneity of the constituent material. I mean that we have a material which is characterized by a set of REVs. But this is our material, it's the same everywhere in the macro scale FEM method. So how to use that? So it's a unique material made of randomly distributed REV members of the same mesoscale set. Okay, so doing this with only two REVs to make it simple. So this is the response of the two of a set of microscale with only two REVs. So these two REVs are the one for 0.4 and the one for 0.6 Clay fraction. I'm reaching the end. So this is the responses that we get. So the soft case is significantly less mechanical properties than the stiff case. And what can we do? We can randomly distribute these two REVs over the finite element, the macro finite element mesh. And this will give us this result. The red curve is the curve obtained by the finite element response of this mesh implementing a set of representative, statistically representative microscale microstructure. Okay, and we see that it falls as can be expected between the two extreme cases. This is the same approach for excavation problem. So here in blue and red we have the two different the two extreme cases of the set, and we see the response in terms of a second invariant of the deviatoric strain, deviatoric strain tensor, and this is the case with the macro scale variability. So, and this is the scale using only a single set, and we see that this is much more smooth as can be expected. Okay, another case which is interesting to notice is that if we take in this case a single REV, but we rotate it randomly in the different part of the specimen, then we get very soon at the beginning of the loading, we get these pictures which are in fact very well representing what can be seen experimentally on the COX, and this is what has been observed by Jaques DESRUES using his true triaxial apparatus, allowing for image correlation and determining the default. So you see the very impressive correspondence of the experimental and modeling picture, taking into account the variability of the constituent material. I think it's and then it's also possible to deal with micro heterogeneous material. This is the case of Volch sandstone, and it's possible to model such a material using the double scale approach. Okay, so conclusions. We have presented the efficient FEM double scale hydromechanical model with non-linearity that allows to introduce the effect of microstructure in the constitutive model. The hydromechanical coupling is introduced at the micro scale, so no need to define effective stress with specific assumptions on the way to define effective stress or permeability. Realistic microstructures can be used even for large microscale boundary value problem using parallelization, of course. If you make it sequentially, it will take a lot of time. But parallelization is something quite easy to perform now. Variability of the microstructure can be taken into account, organized or not, diffuse heterogeneity, or natural bedding. All these things are at hand using this method. FEM and FEM square, multiscale innovative metal are versatile tools that can be adapted to different materials or to the quite open definition of the representative volume element. So you can expect to be able to introduce in the future different kind of specific physical interaction at the microscale, which will be upscaled using this tool directly. And okay, that's it. So that's what I wanted.
Thank you very much. Joel. Questions?
Thank you very much for the nice presentation. I have a question about the numerical calculation scheme.
Sorry, I'm not hearing very well, so can you repeat, please? Thank you.
Sorry. I have a question about the numerical calculation scheme. You mentioned the finite element square. Because in finite element method, we have to solve governing equations in global scale. By using, we have to discretize the governing equation from spatial and the temporal aspects. So, but at local scale, at each Gauss point, we have to update the constitutive equation. So, my question is, how can we solve the constitutive equation at each Gauss point by using Feynman method?
Yeah. At each Gauss point, we have a small scale DL or finite element problem, boundary value problem. Okay. So we solve that. We solve that problem using a finite element, for example. Yeah. So making a Newton-Raphson iterations at a small scale, and then once it's converged at a small scale, we give back the response to the microscale. That's it.
But that means you need to have a very refined mesh in a very local scale. You include these two simulations together at local scale and at a large scale. But it means you have to have refined mesh elements.
Why? There is no reason why. The small scale can be as refined as you want, but you do not need to refine it that much. Because it's a completely independent problem from the macro and you see, the micro problem is in fact the finite element code which is dealing with the micro problem doesn't know it has to give back information to another FEM problem. You see, there is no connection between.
So it's the separated simulation. Yeah. You have a coupling between local and global, the small scale and large scale. So yes. It's a separated simulation.
It is imbricated.
It
is imbricated, right?
Sorry?
It is imbricated. You solve at the micro scale and then you feed back the macro scale.
Well, the information transfer is quite simple. You give the information gradient. As for classical equation, you transmit the deformation gradient to the constitutive equation, it gives back the stress. Okay? This is classical. And this is exactly what does my macroscale numerical process.
Okay, thank you. So my last question is what about the computational efficiency, the computational time for the simulation?
Sorry, I don't follow you. Maybe we can discuss. I don't understand exactly what your point
there is.
But well, I understand it's not easy to admit at first, but it's completely separated while it's running at the same time. So there is a connection through the transfer of information as the classical Coutil equation. That's it.
Okay. I can suggest to continue. Okay. Oh, there is a lot of questions. Okay. Short, please, then always will be. Okay, yes. All right.
I do have a question because at the end you were starting.
Speak close.
Sorry. I have a question because at the end you started to show some results on the Vosges sandstone, right?
On the what?
On the Vosges sandstone. You did some
The
modelization.
Vosges sandstone, yeah.
And so you were showing that you were putting the anisotropy, and you have seen the next in the figure that you were putting two different kinds of material. But before, when you were trying to make the modelization on the claystone, you were saying that the anisotropy is purely geometric. So does it make a difference whether you're putting different layers with different?
Yes. So this is a possible use of a double scale method to specify different REVs for the soft layer and for the hard layer. This can be done with other constitutive equations, nothing special. Then I didn't want it to go to this refinement, but you can also use the statistical way of defining the set of REVs for the different layers. You may have a statistical set for the hard layer, another statistical set coming from the microscale observation for the soft layer. So you have plenty of way of using this method.
The last question for Gilles, and then I suggest you to continue during the break because we are already late.
Thank you, Jacques. I have a question about heterogeneities and calculation.
Can you speak?
I have a question about heterogeneities.
Yeah.
I fully agree that if you want to define, you have to define set of microstructures. But in your calculation, at the end, at the macro scale, you just make one deterministic calculation. So if you want really to handle heterogeneities, at macro scale, you also need to make a stochastic approach.
Yes, so I presented a first case in which we were using the same REV everywhere, even REV with heterogeneity in the REV, but the same everywhere in the macro scale. But then I presented the case with two different REVs, a mix of, okay? But you can use a mix of 1,000 REVs.
Yes, but after you need to make stochastic approach
to
give the result.
Yes.
And it is costly in time because you have to make it. You need to make a lot of computation.
No, not computation. No. You need to analyze some thin sections that our colleagues are doing in Poitiers to extracting the information about the variability of different aspects of the material, and then using the same REV everywhere or different REVs in different places, it doesn't change at all the cost. Not at all, because the REV
in one calculation. But after you need in one calculation. But if you want to take into account heterogeneities, even if you have heterogeneities at low scale, you have also the repartition of your low heterogeneities at larger scale. So after you need to make more calculations.
You're speaking, in that case, you're speaking of the case of organized heterogeneity. So if the heterogeneity is organized, for example, in the Callovo-Oxfordian problem, you may have layers, and then you have one calculation to put your different REVs in the different layers. In the case of the stochastic variation, then you simply to distribute representative REVs, statistically representative REVs over the computer, the macroscale model, and this will give you answer that you don't need to make a lot of computation. Maybe you can make 2 computations in order to see if there is discrepancy, but I think there is not, because statistically it will average. It will have, as I've seen with the hard case, the soft case, and then the mix is somewhere between in the middle. And if I change the distribution, it will not change the middle response. I'm not sure.
I suggest you to really to continue during the coffee break. Thank you very much. So we'll continue this morning session with a talk given by Christian Levy, so professor and lab director at CRG Paris. So, well, Christian.
Okay, so thank you for inviting me for giving this talk. So we switch to reservoir studies now. And in this talk, I'm going to focus on the monitoring of fluid substitution processes in rocks and water leakage. So it's a collaborative work with many people in our university. So you should CY Cergy Paris University, formerly Université de Cergy Grenoble Alpes, at IFP, University of Mons, and CSIRO in Australia. So what is fluid substitution? So 2 examples. This is what happens when you are doing enhanced oil recovery operations in hydrocarbon reservoirs. You inject water into the reservoir in order to push the oil toward the production well, and then you do a kind of fluid substitution because you replace oil by water in the reservoir. The other example is what is going on when you are doing a CO2 sequestration. When you inject the CO2 underground, then you also have fluid substitution, and it's important to be able to monitor the evolution of the CO2 plume, for example, through time, and this can be done using seismic methods. So these are the kinds of things that we are trying to reproduce in the lab. Seismic methods able to monitor this kind of thing. So actually, I broadened a little bit the scope of this presentation. I will start to show you a kind of history of what we have done on these subjects since 20 years now. And then I will focus on examples of fluid substitution and impact on seismic and mechanical problems. So this is the outline of my talk. First, I will show you the early measurements that we have done, very simple experiments using capillary inhibition tests. And then we are going to switch to fluid injection experiments in which we want to reproduce what is going on in these fluid substitution processes in the reservoir at the lab scale. Okay, so let's start with these capillary inhibition tests. These are very simple tests. It's a very low-tech experiment. So you have a sample, a dry sample here that you hook under an electronic scale here to measure the mass. And then you put the bottom of the sample in contact with a water reservoir, and spontaneously the water will rise into the sample due to capillary effects. You can put a camera here to look at the rise of the water at the surface of the sample. And so this is the kind of device that we are using in our lab. So very simple experiments here. For the moment, there's no monitoring, no seismic monitoring for the moment. Just the raw experiment in which we analyze the displacement of air by water during these capillary processes. So these are the kinds of results that you get So you plot the mass intake into the sample during the capillary wise experiment, and you plot it as a function of the square root of time. So why square root of time? Because it's a kind of diffusion process. So it's better to plot it as a function of the square root of time. So theory tells you that if you do this kind of experiment on a single pore or a single tube, you should have a straight line if you plot the mass intake as a function of the square root of time. So the slope of all these curves here is called the capillary coefficient. Definition is here, so it's the slope here, and you divide by the cross section of the sample. So you can see you have different slopes depending on the samples. These are a set of Nubian sandstone from Egypt with different microstructures, different porosity, and you can see that the capillary coefficient changes from one sample to the other. So simple experiment, but quite useful because what we have done, for example, we have made a compilation of this kind of results. So our results from others, and we plotted the capillary coefficient as a function of permeability for all these samples. And you can see that there is quite a nice correlation here, meaning that you have a correlation between this capillary coefficient and permeability. So it's a log-log plot, so it's a power law with an exponent of 2. That means that you can use the capillary coefficient as a proxy for permeability. The experiment is so simple that it's quite useful to have this kind of correlation to estimate an order of magnitude of your permeability. Okay, so then we also made some experiments in samples in which we generated compaction bands. So we took a raw sample of bentile sandstone and we deformed it. First we did the capillary inhibition on the raw material, and then we took the sample and we deformed it in order to generate a compaction band. So these are the acoustic emissions which have been generated during the loading, and you can see that we have generated these compaction bands in the center of the sample. So then we did again these capillary inhibition tests and compared it to the raw samples before inducing the compaction bands. And one result that we have found is that the compaction bands here slows down the capillary front, okay, but the water goes through, so it's not a complete barrier. It doesn't stop the water from moving up, but you have some changes in the shape of the water front. So the compaction bands have some impact, but it's not a barrier to the progression of the fluid. Then the next step was to attach ultrasonic sensors to our sample, so we can control, actually, using seismic methods, the progression of the water into the sample. So we just use classical ultrasonic sensors that we put across a diameter in the middle of the sample. So we use a pulse generator, oscilloscope, and then you can see how the seismic properties are changing during the progression of the inside of the sample. And these are the kind of results that you get. So this is the mass intake during the capillary inhibition. And here, in blue, dark blue, we have the amplitude of the wave, of the P wave, and in this color we have the evolution of the velocity of the P wave. Okay? So this is the kind of result that you can get using these ultrasonic sensors. And a very striking result that we get from the beginning when we did this experiment is that there is a kind of delay between the drop of the amplitude and the drop of the velocity. It doesn't occur at the same time. First you have the amplitude which decreases, and then you have the velocity which decreases after a short kind of delay. So we are going back to this later and try to explain why we have this kind of behavior. The problem with this experiment so far is that we have no information about the fluid distribution inside of the whole sample. So the next step was to do this kind of experiments under a scanner, a medical scanner, industrial scanner, let's say. So we have done this at IFP and at CSIRO. So the idea now is to So you cannot put a balance here because it's not good to put an electronic device under the scanner, obviously. So the sample is put on a kind of frame here, and you make a classical inhibition test, but under the scanner, and you take some images of the center of the sample during the inhibition. Then you can follow the shape of the waterfront and how it goes up into the front. So here you have the results that we got on the Nubian sandstone that I have shown before. And actually, you have many different kind of shapes of this waterfront. Okay. So, for example, you have flat interface like here, so it's blue. When it's red, you have an interface which is curved like this, and when it is green, you have an interface which is curved like this. Okay. So you can have all kinds of different situations depending on the microstructure of your rock. Okay. There's no systematic; it really changes with respect to the microstructure of your material. So it's this is very interesting because when you see what is going on, you have more clue, you have more information to do some modeling or whatever. So I always like to say that seeing is believing. Okay, and final improvement. Now we do this kind of experiments with imaging, but also with acoustic monitoring. Okay, so we use ultrasonic monitoring on 2 planes at different heights in the sample, and we are doing simultaneous imaging of the central cross section as we have done. Okay, so we have imaging and we have the seismic monitoring. Okay, so the imaging part has been done under X-ray beam using a CT scan, classical CT scan, and another technique has been used also is to do this kind of experiments under a neutron beam at the synchrotron in Australia. So this has been done when I was on sabbatical for 6 months in Australia. So this is a device that we are using for the CT scan. So you have your sample here, the transducers which are here, at 2 different levels here, and we image a cross section which is perpendicular to the plane of the sensors, because you cannot put the sensors on the plane where you are doing the imaging under CT scan. So this is a sketch of our devices, 2 sensors, plane 1, plane 2. Okay. So what we get images like this. So when it is bright like this, you have the water which is in this place here. So it's a wet area, let's say. And when it is dark, it's a dry area. So the water hasn't got into this region yet. So at the same time, so we got 1 image here, and we got 2 waveforms. Okay, 1 waveform here, 1 waveform here, and this every 5 seconds. Every 5 seconds, we have 2 waveforms and 1 image. So we can analyze completely what is going on. For the neutron imaging experiments, so we have used this. It has been done by. I didn't do it myself, but by a student who was there. So the setup is the same, two pairs of transducers. The difference is that the sample is not a cylinder, it's a squared cross section. And the other interesting thing is that with neutron imaging, you can image the plane in which you have the sensors. You don't have the same problem as on CT scan. You can have an image with the sensors in the plane of interest. There's no problem with that. The kind of image that you get is this one here. So it's reversed. When you have water, it's dark, and when it is dry, it is bright. Okay, so it's kind of different convention. Here you can see the transducers, which are located on 2 planes on the sample. Okay, so this is a kind of results that we get. So it's a movie. Before starting the movie, I hope it works. I explain what we have. So these are the images here. This is the location of our transducers. And here you have the waveforms on the lower plane and the Fourier transform of the signal, which is here. and here you have the same on the upper plane. Okay, so I will start the movie. Up. So you will see the water which rises here. So it starts to start here, and you can see that the first impact is on the coda wave here. Okay, and then when it comes close to the transducer, you have some impact on the first arrival here. Okay, you see that the amplitude is decreasing a lot from the beginning. Okay, you have a lot of attenuation which is going on, and you have a decrease of you are losing your high frequency. And at the end, basically, your signal is very low frequency. Okay? But what is very, very striking here, it's the big attenuation that you get in this kind of experiment here. So the same here, so the waterfall goes up, you don't see it very well. First, you have the coda, which is impacted, and then you have the first arrival here, which will be impacted. And here you have the decrease of the Fourier transform. You are losing your high frequency, and you at the end remains only low frequency. Okay, so what can we do? What can we do with this? So this is the final result here. So in red it's the original signal, and in dark blue it's the final signal after the end of the experiment. So what can we do with this? We can measure different things. Okay. So we have seen that inhibition has a strong impact on the waveforms in terms of amplitude, phase shift, that means the velocity is changing also, and on the spectral content. You are losing your high frequency, and you at the end you have a low frequency signal. There's not really a shift of the frequency, there's a lowering of the high frequency content until you only have some low frequency. And finally, we have seen that the waveform coda is impacted very early in the process. The waterform is still far away from the transducer. You have the coda waves which are impacted by the inhibition. Okay, so you can do some kind of waveform analysis. So what we have done, I will not go into the details, but what you can do is to separate with the waveform into different wavelets. Okay. So high order wavelets correspond to what we call the coda, and the order 1 and 2 are the first arrivals of the wave. And for each of these wavelets, you can calculate the energy per cycle for all these kind of wavelets. And the interesting thing is, as we have seen, is that from the beginning, so the inhibition starts here, okay, at 0. From the beginning, you lose energy in the coda wave. Okay. So it's quite, it's a kind of precursor signal of the arrival of your waterform. You look at the coda, if the energy is changing, that means that something is getting close to the transducer. And this is very early in the process. It starts right from the beginning. So take-home message, coda energy variation is a precursory signal for the arrival of the fluid form. So it can be used as a kind of criterion to detect some fluid substitution process in your experiment. So we can also measure the velocity and the amplitude. So we have in our system we have an automatic picking of the arrival time here, okay, from which we can calculate the velocity, obviously, and also automatic picking of the first amplitude, okay, the first peak amplitude, which we call A. And what we do generally is to plot the amplitude normalized to the initial amplitude and the velocity normalized to the initial velocity during the process, during the capillary rise into your sample. So this is a typical result here. Again, you see that, so in dashed line you have amplitude, solid lines you have the velocity. Systematically you have the amplitude which decreases first, and then the velocity. You have this decoupling that I have shown before. It's really something which is systematic here. So on the image, you can visualize where the waterform is when the velocity and the amplitude is impacted. Okay, so you can see that here, when the amplitude starts to be impacted, the waterform is quite far away from the transducer plane. Okay, it's something which happens quite early in the process. When you have velocity variation, here the waterfront is very close to the transducers. On the plane 2 again, you have amplitude decrease when the waterfront is here, the sensors are here, okay? And velocity changes when the waterfront is close to the transducer, okay? And this is kind of systematic. You basically always observe this kind of thing. Another example here on a carbonate rock, okay? It's quite systematic. So I won't go. And this is and these are the images that we got from the neutron radiography. Again, you can see that you have a much better resolution of the waterfront geometry. And again, you can see that we have different kind of shapes. It can be very heterogeneous, or it can be flat. You have different kind of geometry for the waterfront during this kind of experiments. So we have a nice collection of data, both on sandstones and carbonate rocks, with which we can play. So we have done a systematic study. From the images, you can measure the distance when you have the amplitude impacted, and you can measure the distance when you have the velocity which is impacted. Okay? So you can generate a lot of data like this, and you can analyze them in a very precise manner. So what are the general conclusions that we draw from this analysis is that first, the P-wave amplitude is systematically impacted by the approaching fluid front before the velocity is. Okay? First, amplitude decreases and then the velocity. The second thing is that when the P-wave velocity drops, the waterfront is far away from the ultrasonic sensors plane. Okay? So this is an example. We have an impact on the amplitude when the waterfront is here. Okay? It's far away. Third conclusion is that the relative variation of the P-wave amplitude is larger than the relative variation of velocity. You have a big impact. You have a big impact on amplitude and a lower impact on velocity, generally. And finally, the P-wave velocity is impacted when the waterfront is located within what we call the Fresnel clearance zone. So maybe you are not familiar with this concept. It's a concept which comes from the propagation of electromagnetic waves. So here you have two antennas, antenna here, okay? And you want to propagate electromagnetic wave from this antenna to this one, okay? So the theory tells you that if you have any obstacles in a volume corresponding to this rugby ball here, then the transmission of the waves will be disturbed. Okay? You will have some perturbation. So you need to calibrate the height of your antennas in order that this volume here doesn't hit the topography of the Earth. Okay? So you can generalize this kind of concept. In our case, so here we have our ultrasonic sensors. We define this Fresnel zone here, which the size of the zone depends on the wavelength of the wave here and the distance between the sensors. And then the idea is to say that when the waterfront hits this volume, then you will have an impact on the velocity. Okay, this is the idea, and it works quite well according to our measurements. So now, what is the reason why the amplitude is decreasing first before the velocity? Okay, if you are using theoretical models, you should have a concomitant, simultaneous change of velocity and amplitude. So what's going on? So we have two possible explanations. Okay, the best candidate for us is the first one, scenario number 1, and we think that the amplitude drop is due to the diffusion of moisture into the sample ahead of the waterfront. Okay, so before the liquid water is coming up, you also have some water vapor, moisture, which is diffusing inside the rock. And this vapor will decrease the surface energy and will affect preferentially the amplitude and not the velocity. This is the assumption that you are making. So we have some clues that this phenomena is working. I have no time to go into the details, but for example, if you say this kind of thing, so you have the diffusion of moisture from the bottom to the sensor plate here. You know the distance, okay, and you know the time at which you have the amplitude which is changing. And from these two parameters, you can estimate an effective diffusion coefficient. You just take the square of the distance and you divide by the time. You have a diffusion coefficient. Okay. So if you do that, if you calculate this effective diffusion coefficient for all our sample set, actually you find that there is a correlation, quite a nice correlation between this effective diffusivity and the permeability of the water. The higher the permeability, the higher the diffusivity, which makes sense. Okay? So we are quite confident that this mechanism is something which can really happen in our sample. So it's interesting because, I mean, we see the correlation here. It's almost power 1, so it's almost linear here. And this is a plot of measured permeability as a function of predicted permeability using this law here. And you can see that we are quite close to the 1-to-1 line here. And the scatter is less than 1 order of magnitude. So if you predict permeability within 1 order of magnitude, usually you are satisfied. Okay? You are happy. You are happy with that. So it's a mean, it's a technique from which you can calculate the permeability from your acoustic velocity data. So it's quite unusual. It's not the kind of thing that we are used to do. The scenario number 2 was suggested by Jeven Kovanichev. So it's a reply to our paper when we published these results. He said, okay, this moisture stuff, it's quite nice, but there is a possible other explanation, and it's quite a smart idea. So we measure the direct P wave here, but you can also have some reflected waves on the interface. Okay, so maybe you can have some constructive. What's the name of this? You can have some constructive interference here. So you sum the reflected wave and the direct wave, and you have this red signal here with a lower amplitude with no change of velocity. Okay. So when he suggested this scenario, he didn't have all the data to calculate everything. So we have all the data, and we try to see if this mechanism is okay. So we can calculate exactly the reflection coefficient. We can calculate the waveform of the reflected wave, and effectively, in some cases it works. Okay, so this is an example where it works. Okay, so it's a Sherwood sandstone here, and you see you have a reduction in amplitude with no change of velocity. But there are very few cases where it works. In the vast majority of cases, it doesn't work because the coefficient of reflection is very small and the delay is too large between the arrival of the P wave, the direct, and the reflected wave. And in this case, you see that at the beginning there's no change at all, so this mechanism doesn't work in this case here. So in general, it doesn't work. In some cases, it works. So it's not a scenario that you can reject. In some cases, it can work for sure. Okay, so now I come to the second part of my talk. And this time we are not doing any more imbibition tests, we are doing injection tests. So we are working in a triaxial vessel. So the sample is inside the jacket here. We have transducers around the sample as usual here. But this time we inject water from the bottom using a pump with controlled pressure. Okay? And we do this either on a sample which is dry, which has air in the pores, or to mimic what is going on in the reservoir. We also do that in a sample which has oil in the pores. Okay? And during the process, we again measure the velocity here across the different planes. And the idea is to check if we can use seismic waves for monitoring this fluid substitution in the reservoir. So we did this kind of experiment of different rocks. Today I will only show an example on the Aubourg chalk. So it's a chalk from the Paris Basin coming from Belgium here. It's a high porosity rock, 43%, and we have done several kinds of experiments on this rock here. This is the location of the sensors. So we have 3 pairs of sensors at different levels. So on the bottom, middle, and top plane here. Okay. So this is the location of our tensor. So the frequency, pulsing frequency is 0.2 megahertz here. So we record the waveforms every minute during the process, during the injection process. Okay? Every minute we have these waveforms that we can analyze. The loading path is the following. First we do a small consolidation stage here, then we load to the target confining pressure, and then we load the sample in a triaxial way. Okay? Until a target differential stress here. Okay? And so, what is the target differential stress? So this is explained here. I have shown this in the short lecture that I did on Monday for those who were here. This rock is prone to water weakening. That means that you have different failure envelopes depending on the fluid that you have in your pores. So in the dry case or in the oil case, you have a large failure envelope. But when the rock is saturated with water, you have a much smaller failure envelope. Okay? So the target for our injection test is the area here between both failure envelopes. Okay? The idea is that if we load the sample here, so assuming that it has oil in the pores, if you load the sample here, you are still stable. Okay, you are below the failure envelope. But as soon as you inject water, you are above the failure envelope of the rock containing water. That means that you probably will have some kind of mechanical instabilities which can develop in your sample. Okay? So the target, the differential stress target is in this gray area here in our experiment. So this is the kind of result that we get. Here you have the volume of water which is injected. Okay. This is the stress. So the stress remains constant during the experiment. There's no change of stress. Everything is constant. Okay. And this is a strain. Okay. So as you can see that when you inject water, the strain is increasing, and at some point you have a really large increase of strain. You have a stress drop. I mean, the system is no more able to sustain the stress. Impossible. And this happens at this level here, which corresponds, in this experiment, I don't know if I have it here, no. This corresponds to a low, let's say, a volume of water, which is low compared to the total volume of pores available in the sample. Okay? That means that it happens quite at the beginning of the injection test. So we have done many of these tests here, and we found a nice correlation between the amount of water that you need to trigger this mechanical instability and the stress level. The higher the stress, the less water you need to trigger the instability. Okay, this is the idea. And if you get closer to the failure envelope, then you need almost to fill completely the sample to have your mechanical instability. These are the kinds of structures which are developing. So again, everything happens in the lower part of the sample. Okay, the mechanical instability is triggered quite early in the process, and you have the lower part of the sample which is damaged. So this is dry samples which have been in which we have injected water, and this is an oil saturated sample in which we have injected water. Okay. So the conclusion here is that water weakening triggers mechanical instabilities under constant stress. This is important. It's just a fluid substitution effect. There's no stress effect here. Okay. And the saturation level needed to trigger failure depends on the applied load. Okay. These are the conclusions of our experiment. Now let's come to the monitoring, fluid monitoring the process. So actually we can separate our data set into two stages. Okay? The stage number 1 corresponds to the fact that you have your water front, which is rising into the sample. Okay? And then we have the classical evolution that we have seen in the experiments before. That means that first you have the amplitude which decreases, and then you have the velocity again. Okay? So it's not very different from what you have. What is kind of different is that first it decreases, then it increases again, and then it goes down. Okay? So it's kind of complicated, more complicated behavior here. But in any case, here what we see is what we can follow here is the moving of the waterfront inside of the sun. Okay? But then, very surprisingly, we had a stage number 2, which happened when the waterfront was above, at the top of the sample. Okay? And here you have a very strange behavior. That means that all the 3 pairs of sensors recorded the same thing, with a drop in amplitude here, a minimum in amplitude, and a kind of S shape in the velocity. So velocity is increasing like that. Okay? And this happens simultaneously on the 3 pairs of sensors. Okay? So it's not a propagation effect, because the water is already on the top. It's something which is different. Okay? So what is it? So if you go back to your textbook, this kind of figures looks like what we have, the figures that you can find when people are talking about relaxation processes. Okay? In which you have a maximum of attenuation here and elastic modulus, which is increasing as an S shape like this. Okay? So this is attenuation. So high attenuation means a low amplitude. Okay? So it's reversed, but this can be explained by using the standard linear solid model, the Zener viscoelastic model, which is a combination of dashpots with given viscosity and springs with different elastic parameters. Classical physics, okay? And you get this kind of evolution. So what is the difference? The difference is that in this representation here, it's a function of the frequency. Okay? You have a change, this kind of change is as a function of frequency. But in our case, the frequency is constant. Okay? It's the pulsing frequency of in our experiment. So we have the evolution as a function of time, whereas here we have the evolution as a function of frequency. That means that in our case, we have a process in which the relaxation frequency is changing with time. We have a process in which the relaxation frequency changes with time. So we need to find a mechanism in which we have this relaxation frequency which can evolve with time. So you can play with this parameter of the Zener model. So these are 3 different experiments in which we have the same kind of behavior. You can find these parameters in order to fit the data, no problem. But this doesn't really solve your question. You don't know what is the mechanism. So you really have to understand what's going on. So one needs to find the physical mechanism which is responsible for the observed relaxation, obviously. And as our working frequency is constant, one needs to find a mechanism where the relaxation frequency is changing with time. Okay? Otherwise, you shouldn't have this kind of evolution. So we tested different assumptions here. The first one is the transition between drained and undrained. Okay? Classical biotheory. Okay? You have a transition from drained to undrained. So this is the relationship that you have to use to calculate the critical frequency, the relaxation frequency. And this gives you a very low frequency, about 2 Hertz, and we are working in the megahertz range. Okay, so this doesn't work. Then you have the squared flow, relaxed, unrelaxed transition. So the relaxation frequency is given by this relationship. And to work in our case, it would require very small aspect ratio, about 10 to the minus 3. And we don't have any clue about the presence of cracks with such low aspect ratio. First, the third assumption is the patchy saturation model, in which you have some patches in which the saturation is low and high, etc. So the relaxation frequency is given by this relationship. And this, if to work in our case, this requires a patch length of 50 microns. And this is quite a nice value because it's larger than the grain size, okay, and smaller than the wavelength. So we are in the good range for this mechanism to work, okay? So we discard these two and we focus now on the patchy saturation model. So this model here, you represent your rock with grains partly saturated with water, and you have some patches of air in your sample. So there is a model in which you simplify this geometry into a bubble, a spherical bubble of air or gas here, and around you have a ring made of saturated porous medium. Okay? So this is the schematic system which is used to develop the model, which has been proposed by White in '75 already. And the patch length here in the equation that I showed before corresponds to the thickness of this ring here. So again, this is a relation that I've shown here. So what happens? So the patch length here, the patch size occurs on the denominator here. When you increase the water saturation, that means that you decrease the size of the gas bubble. And if you decrease the size of the bubble, you increase this length here. And if you increase this length here, you decrease the frequency. So you have a frequency which changes with time because the saturation is changing with time. This is the idea. Okay? And we are really confident that this model can explain our data set. So our interpretation, the relaxation frequency decreases with time because the water saturation is increasing, which makes sense because you inject more and more water into your sample. Okay? So you have an increase of water saturation, which induces a decrease of the relaxation frequency. So this is a small movie. I have almost finished. So this is a movie in which we have this relaxation process. At the beginning, you have a high frequency. You are far away from the frequency of the pulsing here. And when the saturation increases, no, it doesn't work. Yes. So when the saturation increases, you have the shift of this relaxation process, which will impact the system with our frequency, which is here. Okay, so I will not go into the details, but this is the relationship that we are using to account for our results here. The results are the points here, and the prediction of the model is this one. You can see it's not far away. This is the prediction of the model on the evolution of the relaxation frequency as a function of water saturation. So here we have our pulsing frequency, and you can see that the transition will occur here. It corresponds to a saturation of 88%. So below 88% we are in the relaxed regime, and above we are in the unrelaxed regime. So we have the transition between relaxed and unrelaxed regime. In both cases, we are obviously undrained. Okay. I will skip this one, which is just showing that you can modify the model to account for the water weakening, and you have results which are better when you introduce water weakening. Okay, so this is just I write to a conclusion here. From the inhibition test here, we have seen that there is a decoupling between the evolution of the P wave amplitude and velocity. Okay, which can be explained by the moisture diffusion, and this property can be used to predict permeability from P waves attributes, as we have seen. For the injection test, we have evidence on viscoelastic relaxation processes. Increasing the water saturation above 80% induces a transition from relaxed to unrelaxed regime. And finally, the patchy saturation model was improved by adding water weakening effects into the model. And this is work in progress. What we are doing now is to try to simulate the waves in our experiment. Oh, no, it doesn't work. I know, it doesn't work. Anyway, so it's here we are. This is what we are doing now. We have our sensors here, and we calculate the deformation, the displacement field when you are emitting waves And we take into account the reflection on the waterfront and so on to try to better analyze our waveforms. Okay, I will stop here. Thank you very much.
Simon, one short question, please. Yes.
Yeah, concerning the first part of your presentation, I was thinking also about the capillary effect, because the waterfront is not so square as shown by the images. So you have a certain width. That is depending on the pore size distribution in your system. So I've seen a lot of samples that are probably have a broad pore size distribution, and we know that the inhibition is first is larger in the smaller pore. So there is also an effect due to just the petrophysical characteristic of your samples. Have you thought about this, or is it important within?
Well,
you see,
we are aware of this, obviously. This can explain the very different, the heterogeneous shape of our waterfront, but we haven't gone so much further.
It may contribute also to the amplitude decrease first in advance to the velocity. I'm
not really sure, because I mean, on the images you see that the waterfront is very far away from the sensors. Okay?
Yeah. Okay.
So something needs to account for it, which is different from the water, water motion. So our best guess is moisture. Diffusion. Okay.
So it will be short. So the idea, so good morning. The idea is to see how bulk processes influence frictional behaviors of fault, and how bulk processes also influence permeability with respect to faults. So this is work that we have been done at EPFL, and this is mostly the work of Gabriel Meyer and Carolina Giorgietti, that is now at Sapienza University in Rome. So this is just an introduction. So as you know, climate change mitigation strategies such as CO2 sequestration, extraction of less carbon-intensive sources such as geothermal energy, natural gases, are important topics in science that can be partially solved by modern rock mechanics. And in our lab at EPFL, we try to solve this question, which type of energy should be developed in the future, with a big focus on deep geothermal energy. What is the future of and feasibility of carbon capture and storage? What should we do with nuclear waste? And in particular, we work on the risk associated with these new sources of energy. As you can see on the diagram on the left, that most of these questions are related to fluid injection or extraction. So this is the case for CO2, for geothermal energy, for wastewater disposal, for example. However, fluid injection and extraction increase pore pressure over long fault. They can decrease the normal effective stresses, alter the subsurface stresses, alter the chemical and thermal properties of rock, and therefore they can encourage seismicity. And these earthquakes, they nucleate on pre-existing faults, so they are due to slip on fault surfaces. And three parameters are very important to understand what's happening on the fault planes, that are friction, fracture, and geometry. And this is important to understand the physics of both natural and induced earthquakes. And today we'll mostly focus on the geometrical aspect to see how we can connect bulk and fault problems. So more recently, people have tried to engineer reservoirs around the metal-ductic transition. This is one example of concept in Japan for the GPPB project, but it's the same concept for the Hailey DP project, the Newberry volcano in the US. And the way people want to do that is because engineering reservoir in the ductile domain, it will allow a simpler design because we have homogeneous rock properties. We will have a high recovery rate of injected water, a minor impact on shallow hydrothermal system, a large power generation because there is a possibility to exploit supercritical fluids, so fluids with temperature higher than 400 degrees Celsius, 20 MPa of pore pressure. and there is probably a lesser probability for induced earthquakes. So the idea was really to check if there is a less probability to have induced earthquake at the ability, and what is the impact on permeability. So this is just natural data. This is the seismicity in Italy and in Greece in the carbonate sequence. You can see that most of the seismic events around the Mediterranean area are housed in carbonate layers. So I put them on the left, depth versus number of events. You can see that these events are mostly between 4 and 10 kilometer depth. And on top of this, I put the frictional envelope and the flow law in carbonate. And you can see that most of these events are in the semi-brittle domains. But as soon as we enter in the ductile part, it seems that there is a kind of cutoff of seismicity. So maybe this is a nice thing for reservoirs. Maybe we can have a cutoff of seismicity if we really engineer reservoir in the ductile domain. So, but what is ability? So I think you all know that, but rocks undergo a fantastic transformation when their mechanical behavior are subject to stresses at low temperature, pressure, and high strain rate. Generally, we have rocks that are brittle, that are prone to fractures, and we have a deformation that is localized. At high temperature, high pressure, the rock transition into a ductile behavior, where they deform homogeneously, and they flow without fracturing. And this is a very famous paper of Patterson that show from brittle to ductile deformation. So the crust can be divided in two distinct layers. On the top part, we have faulting and cracking, and the stress is localized, and we think that is dilatant, so this is good for reservoirs because we have pores. And the strength is mostly controlled by fault and by friction. And friction, we know that is independent of temperature and rock type. In the second part of the crust, the deformation is probably controlled by crystal plasticity. I think Alexandre knows it much better than me. Strain is homogeneous. Generally, we think that we are isovolumic, meaning that we don't have dilatancy, that the strength is approximated by high temperature flow laws, and we are mostly pressure insensitive. But this reservoir that people want to engineer for geothermal energies, they are probably in between of these two layers in what we call the semi-brittle field. And here is a bit of mess because we have a combination of cataclysmic flows, crystal plasticity, the strain is pressure, temperature, strain rate, water dependent, and we don't know the clear boundaries between the brittle and the ductile domain. So the question we try to answer is how do permeability involve adability, and can earthquake nucleates adability transition, and if so, how does awful deformation, inelastic deformation influence the seismicity? So for this, in the lab, we developed laboratory seismology. It allows to reproduce earthquake under safe and controlled conditions. We try to reproduce pressure, temperature, strain rate. It allows an individual analysis of the physical parameter and the production of a large earthquake catalog without any risk. What is important is that most of the earthquake processes are scale invariant, so we can study them in the lab and try to upscale them at larger scale. So this is the machine we currently have at EPFL. We are able to reproduce this fluid-induced earthquake in the lab from interseismic strain rates 10 to the -9 up to almost co-seismic strain rate 10 to the 2. At in situ and pressure conditions, so pressure up to 10 kilometers. And in particular, we developed two experiments. The first one is this one. This is ISTerre. This is a biaxial machine, so where we can control both the normal stress and the slip velocity. And the particularity of the machine is that we can go in a confining pressure up to 100 MPa, but that is also equipped with 4 linear motors that are connected in parallel, and we can slide at micrometer per second up to meter per second. So we cover the entire range of seismic velocity we have during an earthquake. The second machine you can see here is a machine I developed with Dr. Schubnell. It's a high pressure, high temperature triaxial machine. Is a new generation of the Patterson machine, or old generation, I don't know, because it was not working so well at the beginning. But so with this machine, we are able to go up to 1000 degrees Celsius, 400 MPa. And the particularity of the machine is that we have quite large sample We have 20 millimeter diameter sample and 40 millimeter length. We have also the analog machine that Federica showed you yesterday, and we have a classical triaxial machine. So the first thing we did is to check the permeability evolution at the ability to see if really we can have a reservoir that we can exploit at the ability condition. And for this, we use this high temperature, high pressure triaxial machine. You have the diagram on the left, so the sample is just in gray here in the middle. We have an internal furnace that is in red here. And the furnace and the sample are in a vessel that is filled by a gas that is argon. So with argon, we can go to very high temperature, as I said, 1000 degrees, and pressure up to 400 MPa. One cool thing on the machine is that we have an internal load cell that is just here, very close to the sample, and that we can inject pore pressure that can be water or that can be argon. So what we did with Gabriel is that we tried to do a basic triaxial deformation, but at different temperature, from 200 degrees Celsius up to 800 degrees Celsius. On a long island granite that you can see on the right, the sample is 20 millimeter diameter, and we oppose harmonic pulse in terms of pore fluids to use the harmonic permeability methods developed by Fisher and Patterson, and then changed by Bonnelye. And what you can see on the left is the mechanical curve. So it's simply stress versus strain. And you can see that at 200 and 400 degrees Celsius, the sample is really brittle. We have a huge stress drop, deformation is localized. And then at 600 degrees Celsius, we start to have something that is a bit more ductile, stress drop is a little bit less marked, and we arrive to a constant stress. And at 800 degrees Celsius, we don't have any stress drops. Macroscopically, the sample looks like very homogeneous. Deformation looks like very homogeneous. We have no localization. But surprisingly, when we look at the relative permeability versus strain, what we see is that we have an increasing permeability with strain at high temperature, and we don't have this at low temperature. So when we are at 200, 400 and 600 degrees, the permeability that is quite low, we were in the range of 10 to the minus 22, something like this, meter square, stay almost constant during deformation, but when we are on the ductile regime, we have a very big increase of permeability. And this seems a bit contradictory with result I got before on other type of machine, where when we measure dilatancy, we have the impression that when we enter in the ductile domain, we are mostly like passing from dilatant behavior to compactant behavior. Okay, so it seems a bit strange, and this is true for granite, this is true for basalts, but still, if we look at the temperature we deform, so 800, 700 degrees Celsius, we still have a dilatant, little bit of dilatancy, but much less than 600, 700, so we were not really understanding why we measure a permeability increase under ductile regime when dilatancy seems much higher in the brittle domain. So then we went to the ISTRF and we just CT scan our images, and what we see is that really under brittle domain we have a lot of dilatancy, big cracks, large cracks, but they are not very well connected, especially because we measure permeability just in the axial direction. So, and the fault is oriented at 30 degrees, so we are passing by the matrix, then by the fault, and then by the matrix, but we don't have a lot of cracks. We have cracks that are very well connected along the fault plates, but we have a low permeability. However, in the ductile domain, and it was not a ductile domain accommodated by crystal plasticity, it was both crystal plasticity and diffusive cracking. What we have is that we still have a system that is dilatant, probably lower than what we have in the brittle regime, is what I showed you before, but the cracks are diffusing the rocks, resulting in a high connectivity, at least in the axial direction, and we have a strong permeability enhancement with deformation. And if I make a small sketch, it's a little bit this. At the beginning, we have small cracks in our granites. So when we start to deform them elastically, we start to close them. Then when the cracks start to nucleate and coalesce, the permeability increase. And in the brittle domain, the permeability is mostly controlled by the fault, but in the axial direction, this is not connecting with the top and the bottom of the sample. In the ductile domain, what we have is that we have diffuse cracking, and this makes the permeability higher in the ductile domain, but maybe not along the fault plane. And this is something we are trying to compute with the synchrotron images now. So now I want to move to the second part and more of the aspect on seismicity. And in this case, we don't use the Patterson machine. We use the biaxial shear apparatus that is called ISTEP, that look like that. The apparatus, as I said, is divided in 3 parts. There is all the hydraulics pumps, all the hydraulics pumps that are on the right here. These pumps control the normal stress, the pore fluid pressure, and the confining pressure. We have the vessel in the middle, that is just here, where we can put our samples. And on the left here, you have the linear motors to control the slip velocity. And typically, we have a biaxial configuration with the normal stress that is applied in this direction and the shear stress in this one. The samples are not that big, are 2 centimeters per 2 centimeters. But we can have a normal stress up to 100 MPa, shear stress up to 200 MPa, slip up to 5 centimeters. As I said, we can cover the slip velocity of the entire seismic cycle, micrometer per second up to 0.5 meter per second. Confining pressure 100 MPa, pore fluid pressure 100 MPa, and temperature that is up to 100 MPa. In this case, what we do is that we use a Carrara marble sample, because it's more or less one of the only lithology that under this pressure and temperature condition can fully transition from brittle to ductile. So we use a Carrara marble sample, and we glue a small strain gauge very close to the fault plane just here. So then we run experiments under 2 stress conditions. First condition where we have only 15 MPa confining pressure, a normal stress of 29 MPa, and second experiments where we are under confining pressure of 50 MPa and a normal stress of 95 MPa. And this is 2 different conditions, so we are passing from something that is mostly brittle to something that is semi-brittle, the bulk deformed plastically. So the experiments are made like this. This is the apparent friction coefficient, that is simply the shear stress and the normal stress versus slip. And we have a first elastic deformation until we reach the frictional strength of the fault, and then we slide at a constant shear stress. This for 4.5 millimeters, so it's what we call the running phase. And then we start to increase the velocity by step from 1 to 10,000 micrometers per second. Then we model the velocity steps with rate and state friction laws to access A, B, and DC, so the rate and state parameters. And we use also the strain gauges to compare the results with the encoder measurements that we have outside of the machine. And this allows us to access to strain partitioning. I will show you how we do that. So for those that are not very familiar with rate and state, so this is just the frictional coefficient versus shear displacement. And this is 2 hand members, let's say. When you do that, you have the friction coefficient that first abruptly increase, and this gives you what we call the change in rate, or the A coefficient of the rating state. And then we have an evolution of the friction that is linked what we call as a change in state, and give you the B value of the rating state. And then we can compute what we call the A minus B parameter. And if A minus B is higher than 0, the fault is velocity strengthening. And if A minus B is negative, that means that the fault is velocity weakening. We can also compute what we call the critical distance DC, that is the time to arrive to a new steady state. So this is just a slide. If A minus B is negative, we can have unstable slip that occur, but this is not completely sure. I mean, it can occur. It's velocity weakening, and we can have an earthquake. And if A minus B is positive, we have stable sliding, and we have velocity strengthening, and the fault will creep. Regarding the strain partitioning, this is how we do. So we glue our small strain gauges very close to the fault plane. So this is the gray rectangle that is just here. And we also measure the total shortening with encoders that are a bit far from the sample. If the deformation is mostly slip, what we will see is that when we will plot the local measurement, the local strain versus the total, we will see something that is flat because the deformation is mostly slip on the fault plane and there is nothing on the bulk, so the strain gauges will not see anything. If the deformation is completely accommodated by the bulk, what we will see is that the local and the total measurements will show a slope of 1. So we will be able to know how many percent of deformation is on the fault plane and how many is in the bulk. So we did our velocity step experiments. So this is A minus B and DC versus slip velocity. The black points are for the low confining pressure and normal stress experiments. The gray symbols are for the high confining pressure and high normal stress experiments. And what you see is that they are pretty similar. A minus B increase with slip velocity, and the DC also increase with slip velocity. But what is important to see is that for the high velocity, for the high pressure, normal stress, and confining pressure experiments, you have these 2 stars here, and these are only 2 experiments where we have stick slips, so we have unstable sliding. Even if we have more or less the same A minus B, the same DC, this is only the 2 experiments where we have stick slip. So we were wondering why. So we checked strain partitioning, and this is the percentage of bulk deformation versus velocity. And what you see is that at low normal stress and confining pressure, bulk deformation is almost negligible. You have something around 1%, so everything is on the fault plane. And at high confining pressure and high normal stress, the strain is accommodated both in the bulk and both on the fault plane. And at very low velocity, we have up to 12% deformation that is in the bulk. So we were wondering if it's this bulk deformation that help the instability of the fault, since we have the same, almost same frictional parameters at low normal stress and high normal stress. So it seems that fault instability seems to coincide with off-fault deformation. This off-fault for deformation, for the moment, I don't know if it's elastic, inelastic, crystal plasticity, cracking, whatever. But we know that there is a part of the deformation that is accommodated in the bulk and not on the fault plane. And is when we have this part of deformation in the bulk that we have instability. In the lab, such correlation has already been observed in dolomitic rocks. So François Pastek showed it in 2019, and in marbles, Jérôme Aubry showed it in 2020. And here, what is important to note is that we are at a constant normal stress, okay? And I don't think that this instability is really linked to a normal stress effect. We have a similar trend at low and high normal stress in terms of frictional parameters, so I don't think that is really linked to that, neither to DC, so to a slip effect. So I think it's a strain rate effect or a slip rate effect in the sense that at low velocity, it seems that we have unstable slip, and high velocity we don't. So if it's a strain effect, probably it's plastic deformation in the bulk that help instability of the fault. So then what we do is that we look at this 2 velocity when we have stick slips. So we plot the stick slip data for the velocity at 3 micrometers per second. The stick slip period is in white, the slip period is in gray, and what you can see is that during the slip period, 100% of the strain is accommodated on the fault, but during the stick period, what we have is a delocalization of the strain from the bulk, and then it relocalizes on the fault, and it delocalizes, and it relocalizes, and it delocalizes from 100% to 0%. So it's not the 12% I show you, but really if we have a seismic cycle, we have something that is a volumic process from deformation completely accommodated in the bulk to something completely on the fault. And it seems that what happened in the bulk influences the stability of what is in the fault. For the moment, we are not sure of what is the nature of this strain, if it's a local elasticity that is not the same as what we have on the fault, or if it's inelastic damage, and at this pressure and temperature, for example, it could be twinning on calcite. This remains us natural evidence. This is the Prague earthquake sequence 2011 wastewater injection in reservoir with 3 magnitude 5 earthquakes, higher than 3 magnitude 5 earthquakes, where what they have seen is that there is kind of relocalization of the first shock before the main events on the fault. So this is the absolute distance from the fault plane and time to the main events, and you can see that it seems that there is a relocalization of this force shock events to the fault plane. This has been also seen on the ridge crest earthquakes. So for the moment we are a little bit here, where we what is really the effect of delocalized strains on fault stability. This is something that we need to better understand, but we have an hypothesis that is a change in local stiffness and a competition between the critical stiffness of the fault and the stiffness in the surrounding medium. And in particular, when you start to have inelastic deformation, you will probably reduce the stiffness around the fault, and then the available energy that you can store will be lower, and probably you can have a competition so between the cassé, the critical stiffness, and the stiffness around, and at some point you can have a K that is lower than cassé, and you can destabilize a fault, but the fault needs to be under unconditionally unstable behavior, so with A minus B that is lower than 0. So, conclusion, I think we try to understand a little bit how bulk properties influence permeability and earthquake, and what you have seen is that we cannot really decouple what's happening on the fault and what's happening in the bulk. Very often in the lab, and I'm doing it, I'm considering a fault as a 2D system, not a 3D system, and here I think it's really important to understand that at the end we are not playing with a 2D system but a 3D one, that permeability can increase in the ductile regime, at least if you measure one direction permeability, because if you have diffusive cracking, then you have a better connectivity between cracks and you can enhance permeability, at least with deformation, and that earthquake is really a 3D process, and bulk elastic deformation can favor faulting stability. And I thank you for your attention.
Thank you very much, Marie, for this extremely interesting presentation. There is time for questions. Jean?
Thank you, Marie, for the very interesting presentation. But this increase in permeability, such at great depth, do we have some evidence that it could be sufficient to have efficient geothermal there? And how would you control the flow, the flow path?
Yeah. So I show you the relative permeability, because if I show you the real permeability, we are around 10 to the minus 21. So I don't think that it will be sufficient. But it's still curious to see that it can increase in the ductile domain, and I was really not guessing it. Looking at the dilatancy data, I was really thinking that we will have a strong decrease of permeability. It was mostly calibration data, I would say. I was not really expecting that. And it was funny to see that the permeability increased with deformation in the ductile and not in the brittle domain. But I don't think that is sufficient to have reservoirs.
And also the difficulty to drill.
Yeah.
At the depth.
Yes.
Excellent.
In your stress strain curve, with the granite stress strain curve that you showed at the beginning, so the one at 600 degrees showed a very, very different behavior. Is this systematic? The Young's modulus is very different.
Yeah. So this is the improvement of the technique to rectify the samples. Because I think here, because the samples are quite small, the machine is not very stiff, and the big issue is to be very accurate with the sample preparation. And as soon as there is a few micrometers of difference, then you close the cracks between the piston and the sample, and you change the initial stiffness, and this cannot really be calibrated because it's really linked to sample preparation. So at the beginning we were just rectifying the sample with a milling machine, and now we use a lathe, and it's much better. So yes, it's not reproducible. I don't think that is a systematic behavior. I think it's an issue of sample preparation.
Okay, so it's not because the other possibility would have been that you're observing the quartz transition, the alpha beta quartz.
If you want, I can try to redo them and I will tell you. But we really changed the way to prepare the sample, really to have to minimize to maximize the parallelism between the two surfaces of the sample. But maybe I can check again.
Don't we have some partial melting at the conduit already?
Water that we used was fluid that we used was Armand. So I think with water, yes, because it will start around 657. But I think under dry condition with argon, we are at the limit. The biotypes start to. Yes.
So may this influence on how this diffuse microcracking? The fact that you have this local.
Well, I don't think that on the permeability measurement it will change something, but on the mechanical behavior, I believe it will change something, yes. But not on the permeability. I think these are very long tests in the sense that I didn't tell you, but we run them at 10-6. The samples are long, so this is 24 hours. We started the lab because we wanted to have a very low frequency oscillation to be accurate. I mean, they are not very permeable, so our data really difficult to get. I have to say, but yes, I think they influence the mechanical behavior, but I'm not sure the permeability.
Okay. There was another question. Somebody was. Okay. Right.
So when you discuss about the influence of what is happening around the fault of the whole bulk or the damage zone, whatever you want to call it, it's of course really interesting, and we all know that the damage zone will have an influence, but it's a little bit one that you don't see much difference between the beginning of your experiment, where your sample is actually fully intact, and so you shouldn't have a damage zone, and the rest of the experiment.
Yeah, because I think here is not really a damage zone that matters, but is really the strain accommodated plastically in the bulk. But you are right, I think locally, if I have a strain gauges that is even closer to the fault plane, I will see something. But here we were still 2 millimeters from the fault plane, so I think what we measure is mostly deformation of the bulk.
So some plastic energy that is stored in the bulk, and nothing linked to the...
But I think this will add on the top an effect on the stiffness, because you will accumulate damage, so you will decrease even more the stiffness of the surrounding medium around the fault, and even more you will have an unstable regime when you are unconditionally stable. So yes, it will just add something on the top. Then we start with very smooth sample, so I don't think that we induce a lot of awful damage like we can have in an earthquake in natural one.
Thank you. Let's thank all.
So this talk will not be about earth mechanics, but more about petrophysics. And so I will start my presentation with some, by recalling you some numbers, big numbers. The
the CO2 storage potential worldwide is estimated to about 8,000 minimum estimation, 8,000 to 35,000 gigatons. And these are located nicely, actually, relatively nicely in a region where it is needed to do storage. China, India, Europe is, yes, reasonably well, have reasonable storage capacity in the United States. And so, if you compare these numbers to the cumulative anthropogenic CO2 production up to now, about 2,000 gigatons. Compare it also to the actual CO2 production of 40 gigatons per year. So the storage capacity, even in the lower bound, is far larger than what we produce. So there's some reasons to be optimistic. So this number also is actually depends on the scenario that you would implement in the future by 2100. But okay, so there is some reason to be optimistic because physically there is a space to do the storage. However, up to now is not exactly 2023, but it's 2019. So there is not a lot of things going on. So you have a list of well-known projects here. And so the first one is the well-known Schneider case. But if you see the numbers here, so you can inject in one well or maybe several wells 1 million tons per year. So there is an order of magnitude needed to inject gigatons. So even if you do the total amount, it's 30 million, this kind of order of magnitude. So, and actually a project, typically a project, is now designed to inject 1 million tons per year in one well or several wells. So a very large deployment is needed if you want to reach the gigaton or 40 gigatons. So you see the problem solved. This is a reason to be pessimistic, but okay, I'll let you decide if you should be pessimistic or optimistic. And so, well, for the CO2 storage in aquifer, so I'm talking about sedimentary formation in saline aquifer. Of course, in the industry, they are starting to inject in depleted gas field or oil and gas fields, but this is not enough, far not enough to. But it will start. The industry will start with this easy case. So here, the issue are well known for the CO2 storage. First, of course, in CO2 injectivity, so the well is essential. You're not going to have a lot of wells, one or two maybe, and so injectivity is critical, and you have some reasons for the injectivity to decrease, especially the rock drying, the salt deposits, because you're flowing a gas, so you will dry the surrounding of the well, and then have potentially injectivity problem. So this could be solved by injecting fresh water and also, but you have to stop operations. You have also, of course, the mineral dissolution precipitation. And so well integrity after, so you have to have a good cements. The cement has to be compatible with CO2. So the interface cement and steel should be well designed. What I will talk about the CO2 capacity. So CO2 capacity is actually depending on the structural, the geometry of the system. So you have to be careful so there is no overspill to region far away from the injecting well. You have to be careful about the presence of fault in which the CO2 could flow up to the surface and so on. And finally, in any case, if you have CO2 at the surface, you could have a CO2 leakage. CO2 leakage is a minor problem, in my opinion, but the brine production may be a problem, because at the scale of a basin, you may actually, if you put pressure at one point, so only 50 years later, you may produce brine very far away from the injection at the basin scale. So, for example, you inject in Paris, you would produce brine in the Vosges region. So that's not impossible. And this depends on the structure of the aquifers. Okay, so when on problems. So what should be done with a general workflow here, in which you start with characterization at the lab, and so you have to do geology, petrophysics, geochemistry, geomechanics, and here we heard a lot about geomechanics here. And then the next step is to build a geological model, not only at the scale of the reservoir, but probably at the basin scale, to see the pressure far from the reservoir. To see if the system is closed, or if it's open or semi-closed, and there's an issue about this. And in the end, this is what we do. My colleague in reservoir engineering do the simulation, simulation of injection of CO2. And so that gives you the dynamic storage capacity estimation. You can actually design the optimum flow rate, design the pressure management, how much pressure should I input, number of wells. And this, in the end, this software can be quite complicated. It may include not only two-phase flow, but geochemistry, geomechanics. You may want to model the entire system up to the surface. So if you want to predict the elevation of the surface, for example, in Algeria, there was an elevation of a few centimeters at the surface, and that could be measured by satellite. So, but this workflow is actually not simple, but it is usual in the oil and gas industry. So let's go to some details now about what should be required. And here I take a very small part of the problem is to take the petrophysical point of view. So let's say at least what I need to do the simulation, and this is really basic. For the weather, I need porosity and permeability. It seems to be obvious, but not really. And capillary pressure and relative permeability in drainage and imbibition. So this way we'll be able to deal with the trapping, these two mechanisms of trapping, residual CO2 trapping and structural stratigraphic trapping. These are the most important trapping mechanism that you are using. And for the capoc, for safety, at least the gas entry pressure. And so you'll be able to manage the pressure in the reservoir. And permeability in case you have a heterogeneous caprock. And if you have a partial invasion of CO2 into the caprock. So let's look a little bit about the methodology. So permeability, so it's a very trivial measurement. You all know that measuring permeability in the range of 100 millidarcy is really trivial. I mean, you inject you inject a flow rate and measure a pressure drop, but it's not the case when you go down to nanodarcy, to 10 to minus 21 meters squared, for example. And here I'm showing the push-pull technique that we use now. Not every day, but when we need. So actually, you're going to put two pumps upstream and downstream, and two pressure sensors. And the sample, of course, you control the stress, confined stress, you control the pore pressure, everything. And this is actually a nice technique to measure these low permeability systems. Here, but what you need is to have extremely accurate pumps. You see the range here in CC. So you're going to have to derive when both flow rates are stable here. That means that all the molecules are moving into the porous medium. But you don't flow a lot. Usually in a normal experiment, you flow 1 pore volume, 2 pore volume. Here you flow almost nothing. But since the pump upstream and downstream giving the same results, you know that all the fluids, all the molecules are moving in the fluid. Sorry, but you displace extremely little volume. And so you do it for 3 pressures difference. And you get for example, for 3 points, you get permeability. For example, here in this case, 28 nanodarcy or 26.8. So you have a nice error bar on your system. So the price to pay for these experiments, you see it takes only 9 hours. But what I don't tell you is that it takes at least 2 weeks to prepare the sample, because you can obtain this result only if you have no air at all. Otherwise, you don't have the same flow rate at both upstream and downstream, for sure. So it takes a lot of time to, and I should mention also, of course, these small volumes you need to stabilize the temperature very nicely. It's something like 0.1 degree. So if you have a lot of inertia in your system, the cell is big, it's okay. So I recommend you to, we did, there's a nice benchmark actually managed by Christian David in 2018. So we did measure, several labs did measure the low permeability system on fracture system, granite and so on. And we compare all the methods, and it was nice results. Actually, we agreed. I think I remember we agreed almost, despite the difference in the method. And so, what is very popular in many labs also to use unsteady state pulse decay. But there is some ambiguity here, because when you use this pulse decay, you have 2 parameters to fit: the storage factor and the permeability. So, well, if you want to be very exact, you cannot really fit. You could fit both parameters, but you have some uncertainties. So it's better to, for example, to do the previous experiment with a steady state experiment and fit then the storage factor, and you get this kind of numbers, which are classical. In general, the works, you know the type of works we have, so the storage factor is could be set in a given range. But you see that the unsteady state measurement is not much faster than the steady state. And for these experiments, it's the same. You need 2 weeks to saturate, perfectly saturate the system. So because people believe usually that the steady state experiment is the unsteady state is much faster. That is not true. It depends on your equipment. Okay. Yes, and finally the gas energy pressure. This is actually a time-consuming experiment. So you can use a step-by-step method, and you see it takes several days. Because again, you have to detect. You maintain the downstream pressure with a liquid. The system is fully saturated, and then you put a gas pressure at the face of the inlet face of the sample, and you increase the pressure and wait until you displace the system, displace some fluid, and takes of course it's to detect the time when you have the entry is relatively difficult in general. So it's time consuming. So but okay. So this is related to the permeability, of course, because entry pressure is related to some pore size, there's minimum, some average pore size. Permeability is related to the average pore size. So normally you find a good correlation between gas entry pressure and intrinsic permeability. You can also use this kind of relationship, but with not a lot of correlation in the literature. Okay, so I pointed out some two difficulties for permeability and cap permeability. Now I'm going to give you some details about the capillary pressure and relative permeability measurements. So here, what you need to do is a simulation. You need to determine gas-water capillary pressure and relative permeability. And you have not only the drainage, but you have the individual cycle. And you have the very important numbers here. It's irreducible water saturation, which is actually not well defined physically. It's a point at which you have a kind of asymptotic behavior of the capillary pressure curve, but of course, if you increase the pressure very large, you can go to zero. So it is defined. It's poorly defined at a given pressure. So this pressure is related to the pressure that you can impose in the field. For example, in mercury injection, you don't see really nicely this asymptotic behavior. And so normally you have the same for the drainage, relative permeability, and drainage and emission. And normally you should also introduce all the cycle, partial cycle. If you stop here and if you stop here, so you have another curve. So you have a multiple curve. So in principle, it's quite complicated. So normally it's expensive measurements. So PC and KR are deduced from two different experiments. Typically porous plates, what you call porous plate experiments, and KR from core flooding experiments. You have fundamental difficulties actually, because the gas is the mobility ratio is unfavorable, so you have instabilities due to this effect. So you may have a digitation in your core. So you need usually a very long core. So long core are not so easy to get from the well and so on. So not so easy. So what you suggest as an alternative is a centrifuge technique, in which you can measure actually PC and KR together. So it's a little bit of a specific centrifuge, special centrifuge. So in centrifuge technique, you spin a sample, in this case in the air, so the sample is fully saturated. And so the capillary pressure at a given radius of rotation here is given by this formula. It's proportional to the square of the rotation speed here, omega squared, and to the density difference. So for water and gas, there is a large difference. So it's easy to perform with gas. You could use it. You could make it with CO2 if you want. Usually it's with air. And in this system, we have a rotating contact in which you can follow the production of water during centrifugation. So these are indeed not very. Only a few labs have this kind of technology, but it's very useful, because you can do extremely nice experiments. So you do multi-speed, multi-sample experiments, and so this is the brine production measured as a function of time. So you spin it without interruption during quite a week. Huh? And each stability point here is actually a speed of rotation. And you see the dashed line actually is a numerical simulation of the production that I will talk a little bit later. But if you use these points here, so we have 4 samples in this system, and so you can just deduce the capillary pressure curve for the 4 samples here. So we had, in this case, one sample was different from the 3 others. And you see for these 3 samples that are close in terms of facial analysis, you have a good repeatability. So two different systems. So you see that this is a sandstone situation. So the reduced water saturation due to the amount of clay in the system. The explanation is very clear. So you get the PC curve, and with the same experiment, by analyzing the transient display saturation value, the speed at which you go from one equilibrium to another, you can get the relative permeability curve. And here, there's also some details, important details for the experts. So if you use simple power law, doesn't really match. So for me, this is a very good match because it's not so easy to match with this kind of experiments. So we had to use the let function. That's a model, a very versatile model of relative permeability, in which you have 3 parameters only. So this way we could actually really nicely fit the system. So again, you have a very nice, almost nice coherence between the three similar samples, and this sample is very different. So you understand here why you need dynamic storage capacity assessment, because you're going to reach this saturation. So you're not going to be able to put CO2 in this porosity, in the small pores, that's for sure. But even to reach the reducible saturation, it will be very difficult. You need to put a lot of pressure, differential pressure, and in practice, it depends on the situation. Close to the well, you're going to be close to reducible, indeed, and even drive the system down to 0. But far from the well, it depends on the pressure, it depends on the geometry, the layering, and so on. So it is just estimating the storage capacity by taking the whole volume, multiplied by the porosity, multiplied by some factor, which is a magic factor, is quite uncertain. Normally, if you want to work properly, you need to do a simulation. And even the storage capacity will depend on the number of wells that you implement, the pressure you're going to put. So the storage capacity is not such an easy number to estimate. Okay, let me know when. So what we collect in this single experiments, so we don't collect everything, of course, but we collect some important part of the curves during each. This number, at the end of the experiments, you can actually put the sample back in water and measure residual gas saturation. You collect this number, you collect one curve. And this is a very good start to do the simulation, because honestly, not all the curves are very important in the simulation or very sensitive in the simulations. But this number is extremely important. So I should mention that the acquisition of this entire set of curves represents a significant effort. With essentially the financial effort, because not all the labs can do properly this kind of description. But at least you have a good start. Now I would like to make a small focus on permeability derived from nuclear magnetic resonance. It is actually in relation to the work we did with Pierre Birest and Siva. So getting permeability, in situ permeability, has been a challenge since many years. And here, especially in carbonates, in which basically you have very little relationship between permeability and porosity. and this is a famous work of Lucia. And even if this is old, this kind of relationship have not been. There's no real progress in this relationship because it is by nature it is poorly collected. Permeability is poorly connected to porosity in carbonate system. So the way to get around is to use nuclear magnetic resonance. So I need to introduce a little bit what we do in nuclear magnetic resonance very shortly, so you understand what is done. So in nuclear magnetic resonance, you measure magnetization, and you measure a decrease of magnetization as a function of time after an excitation at time 0. So this is done by an apparatus that I will describe later. So you do a inverse Laplace transform to get the time scale of decay, and you get a distribution of relaxation time. And so basically, in this distribution, the small pores are at small relaxation time, and the large pores are at large relaxation time. And the area under the curve is the water volume. You can scale it to the porosity later. If it's easy, it can be easily done. So you have a measurement sensitive to the water volume or to the porosity if you want. So the measurement takes in the lab a second, mostly a minute. In the log, in situ, it takes seconds. So the relaxation time can be interpreted as a pore size, as I said. So in the range maybe 1 to 10 milliseconds, it's clay or macroporosity, intergranular porosity for above, and then at a very large relaxation time, it's bulk water. So you still collect even if you have a new emission by bulk fluid. You always collect the exact amount of fluid that is in the system, and you have a good measurement of porosity. So if you have water, this is in case you have water in your system, and if you have hydrocarbon, you have also a measure of viscosity. So it's not a case, it's not of interest, but you have a relationship with inverse of viscosity. So for example, you can detect bitumen or organic matter in some system because they will behave in this range of relaxation time. So if you have a saturated system, for example, this is in the Andra in the Bull region. That's one well we looked in the past with Andra, and this is actually the Cox formation. So it's really obvious. It's really obvious to read this kind of logging data because the small relaxation time corresponds to the clays, and here as soon as you go to another formation, you have, for example, in this case, carbonates. It's really moving to larger values. So it's straightforward to read, and you get the porosity at the same time. So the porosity is not so obvious. You don't see this so obviously that in this distribution. So this is, it's really important logging data for me, in addition to neutron and so on. And so how do we measure this in the lab? So we measure this with small tools actually. You see it's on tabletop instruments, running with permanent magnets. And in the well, it's the same, it's permanent magnets tool. So you have several designs, but basically you have, for example, in this design, you have an opposite magnet in which you measure the sensitive region will be here at where the B1 field, oscillating field, will be orthogonal to the permanent magnet field, and so you're measuring close to the well a few centimeters from the borehole. So you are in the invaded region, so you have to be careful with the type of pad when you interpret this measurement. So commercially, it is done on a routine basis. And so, for example, from Schlumberger here, you have a porosity and different fraction of porosity occupied by water and oil. You have the CMR permeability deduced from the distribution, and you have this distribution here, and you have in addition neutron density, resistivity, and so on. Okay, so you know what is done, and we'd like to show you a case. Yes, first, how do we get the NMR permeability? So it is a correlation, but not a true correlation. It has some fundamental theoretical basis. Here, so the general approach is to relate permeability to T2 and porosity to some power law, to some exponent here, with a prefactor C. So T2 represents one characteristic pore size. For example, you could take the log mean value of the pore size, or you could take the mode, the dominant pore size, or you could take, if you have a system, a carbonate system, the matrix, and so on. So you have several choices in the distribution. So phi total porosity here could be also micro porosity, could be something else, and C, A, and B must be adjusted if you want to do a proper work on lab measurements. So there exists some default values. So what the people in the logging industry are doing, they're giving you CMR permeability. They have A equal 2, B equal 4, and the C is adjusted if it's a carbonate system with a one value of C, if it's a sandstone system with another value of C. So how does it come from? This equation, actually, you can show from very old work actually that the permeability is related to the grain size square and to some porosity to the power 4. Exactly, you may need to introduce a residual porosity when you have, for example, quartz wharf in your system. But basically, you retrieve these two exponents, and you're making a kind of relationship between grain size and pore size. And of course, this is working quite nicely in sandstones, because you always have, you very often have a relation between grain size and pore size in sandstones, modulated by the amount of clays, of course. But in carbonates, this relationship is lost because of the agenetic dissolution precipitation effect. And so this is why essentially porosity prediction of permeability in carbonates is difficult, even with this information of NMR. And so we just to show you a recent case study in which we did, it was actually in a geothermal context. Yes, this is actually in Paris region, and for the Dogger formation, carbonate formation. And I would like to open a little parenthesis. You see a lot of doublets here. These are the number of doublets developed since the 80s, 70s. And actually there's no petrophysical data published for the Dogger formation. And they all use the Dogger formation, something like 1500 meter deep. And it's quite, I was quite amazed because they don't need actually this kind of data. They even ask why we need to measure permeability accurately. But okay, so it's an example of a technology developed without any detailed understanding of the formation. It's quite surprising. Okay, so I close the parenthesis. Okay, so we had the chance to have, we were lucky to have cores and analogs, and we could do a very nice job here. I have to say that it was funded by the state, by ISTerre. Of course, because the industry will not do this kind of advanced work. And so this is actually lab data presented as a log data. And so you see the distribution measured in in the lab. So each color corresponds to a facies. And well, we have basically two facies according to the geologist, but actually it's quite obvious that this one and the yellow one are relatively similar to yes, okay, they can be grouped together because so two facies, two permeable facies, two relatively non-permeable facies. So here we measure porosity, water permeability. Yeah, we did also study this formation factor, but I will not talk about this. Okay, so this is actually what should be done on a regular basis, facies analysis, core measurements. For me, this is the standard. And so we try several permeability correlations. So first, of course, the water permeability versus porosity. So here you find the three classes defined by Lucia, based on the size of the grains and so on. And so not very good. So the exponent here n is actually of the order of 9. So it means that water permeability is poorly correlated to porosity because you have to increase the sensitivity to porosity to an extreme. So this power 9 is not, for me, it's not physical. And the standard deviation is a factor of 4.5. So that means the predicted permeability would be divided by 4.5 or multiplied by 4.5 statistically. And these are the error bars here. So okay, now let's look at the permeability that you get from in the log from the log data by default. Power exponent 4 and 2 and C equal 4. So, well, not a great improvement because you still have standard an error factor of 4.3. And now, what should be done? And what I always said, you should actually calibrate these exponents here. So you find 6 and 1.8, 6.3, and so you decrease actually a little bit the error factor. But finally, you should I forgot to mention here. There is a classical behavior of carbonates here. You see that this facies here, the brown one, has a permeability, almost constant permeability, and the porosity doesn't vary. So this is a very classical behavior of carbonate system. And so finally, what we found is just related to water permeability to microporosity. And the microporosity is amount you calculate this amount by using NMR because the distribution is bimodal, so you select only the highest modes. So uncertainty factor is reduced from 4.5 down to 2.6, which is probably the best you can do. Predicting permeability by a factor of 2.6 for me is quite good. And here comes the relationship with Pierre Beres, because I had the opportunity to work with Siva and Pierre about this WT log. I think there will be some talks tomorrow about this technique. So I was involved in this work because yes, we compared actually the NMR data with this permeability log, which will be explained probably tomorrow, and so which is derived from the tightness test that we presented yesterday. Right? And so we could compare this. So it gives you a continuous estimation of permeability by analyzing the leak into the formation, the leak into the formation, and we could really correlate the variation of permeability obtained by NMR not the absolute value, but the variation, with the variation obtained from the derivative log. And now this is dating from 2017, but now there's much more publication. Where is Christian? Antoine Jacques now is. There's more publication about this technique. I learned that this is now will be implemented in Schlumberger to give permeability continuously. It's maybe even better than NMR. So. Okay. Another use, so there's still another use of NMR. You can actually deduce irreducible water saturation for CO2 applications. And so this needs a calibration. You can use standard numbers, some standard cutoff, or you can calibrate. So here the dashed line here gives you the amount of this is the sandstone case, the amount of clay in the system, because these are small pores, and this is actually deduced from a measurement. And you can actually in your log, you can actually deduce this is a sandstone case. The reducible water saturation is a function of height, and this is actually an example. Also here you have this is M like mudstone. This is cementous sandstone. This is sandstone. Cementous sandstone is kind of a quick facious analysis, and so you can see that the irreducible water saturation will vary as a function of height here, from 0.2 a little bit from 0.4 here. And actually, in the mudstone, of course, you will not be able to put some CO2. It's a cap rock actually, and it's quite nicely you can obtain this. And we had only two calibration points. Doesn't need a lot of effort in the lab in general. Well, so my conclusion and maybe final remarks. So CO2 is indeed CO2 storage is indeed a major technology. But in general, saline aquifer are poorly known, and it will need quite a lot of not exploration but characterization efforts. You have a large chance in general of techniques and logic techniques available from the oil and gas technique. So it's up to you to choose the best one. So and the most effective in terms of cost. For sure. One big issue is we need cores, otherwise, if the first step in my workflow is not, there's nothing, no data, I mean the output in the simulation will be, for me, not really pertinent. So it's, you need to do some coring. It must be included in the course of the well. I discussed this just at the lunch about this. Otherwise, you get not really. You can only do scenario, different scenarios, and you cannot really do predictive simulations. And the caprock is also an issue in general. Nobody is scoring the caprock. It's a well-known problem because it's the oil and gas industry very little is known. But since the gas shale production, much more is known for tight porous media, and the techniques are available to characterize the caprocks. So thank you.
Anyone have questions? Do you know some experimental device which couple NMR measurement and dynamic or static mechanical measurements?
It has been done. You can implement in an MR device a cell which you confine the system. It could be a 3-axis cell maybe. It has been done, but it's variation of pore volume. If you have an unconsolidated sand, it's really nicely observe the behavior of your system. But if you have a consolidated system, the pore volume variation are often very, very, very tiny. So it's not, I would say, you don't see the volume to surface ratio, yes. So the volume, you will have a good measurement of volume, but the volume to surface ratio may not vary so much.
Even if there is
Yeah, but if you compress the system, the volume, if you compress it a bit, it doesn't really vary.
Even if there is a damage effect?
So, what is nice is to couple NMR with a reactive system, bicarbonate, so you inject acid, so then what is going to happen, the surface will be etched. I mean, you're going to produce a lot more surface, maybe a factor 2. And that's going to decrease the your T2 relaxation by 2. So it will be extremely sensitive to the surface roughness. So you could use it you could even not vary the porosity and vary the surface roughness. And we have a good indication of this kind of process in the lab.
Okay, so thank you very much, Philippe. I am going to present you some works on hydromechanical cohesive zone model for fracture propagation and fault activation in reservoir rocks. Because this gathering is in the memory of Pierre Berest, let me tell a few words about him and my experience with him. I met Pierre Berest in 1986, so 37 years ago, when I was looking for a PhD thesis, and I came here to École Polytechnique to see him. He had proposed a PhD on the topic of la rhéologie du sel-gemme et les cavernes de sel, which seemed to me very strange at that time, rock salt rheology and salt caverns. And so I came here and I met him and also his inseparable colleague, Mehdi Gourechi, who is here now. And Pierre Berest explained me this topic, and I like it immediately. He was able to share and transmit his enthusiasm for salt caverns and rock salt. And so I accepted the proposition. He accepted me as PhD student. I think I was his first PhD student. And so it was the start of 36 years of collaboration, because I stayed here for 16 years, and when I left, went to LCPC and École Polytechnique, we continue to have collaborations with Pierre for different topics related to PhD thesis and also for teaching at the École des Ponts. Yesterday, many people talked about Pierre and his scientific skills, smartness, and also his very kind and soft character, and also his generosity to share his knowledge and ideas. And I shared with him interest for analytical solutions and mathematical formulation of the problems and so on. And I was really impressed also by his scientific mathematical elegance to deal with the problems. And every simple equation had for him a very deep physical meaning and so on. He has his own style to interpret, to deal with mathematical problems and to solve them and to interpret them and so on. And so really I was interested. He was for me always the symbol of scientific elegance. I can say. So with him I started working on salt caverns and salt mechanics. I worked mainly on creep of salt. It was the topic of my PhD thesis, but also I was interested on the cracking of salt polycrystals. And this was determinant for all my future research career, because from that time I has always been working on cracks and fractures and faults and all type of discontinuities in rocks and rock masses and geological formations, and the mathematical, numerical modeling. And this explains also the work I am presenting to you today. So let's go on to the topic of this presentation. So we need to model the coupled flow and deformation in fractured porous media for different applications. Hydraulic fracturing, natural fracturing in sedimentary basins, we discover it by an example here, but also for fault activation. Also for desiccation cracking in soils. There are the same concepts, physical, mechanical concepts, and also numerical methods and tools which are needed to these problems also, shrinkage cracking in concrete and so on. Some main issues in this domain are first, how to represent fracture propagation. It is a very real difficulty. Also, this will be the main topic of my presentation here. Also, hydraulic flow in fracture and porous matrix and mass exchange between them. Also, the mechanical effect of the pressure in the fractures. We discovered that there are some difficulties to represent it in some cases. And also, in this field of modeling, all we can do or not do is really determined by the numerical tools we available for us, and also especially meshing tools for finite element methods. And because I started my works with this problem, so I first give a few explanation on this. So for fractured rocks and modeling with finite element methods, zero thickness joint element was proposed very early by Goodman to represent rock joints in rock masses and stability of rock masses and so on. So these are 4.0 thickness, 4 nodes, 0 thickness elements that you insert in your finite element method, and you assign to them different constitutive models, mainly for stability of rock masses, and elastoplastic model with more Coulomb criterion with cohesion C and friction angle, and it is sufficient to discuss stability of rock masses. But the use of these elements had always been limited to very simple cases of fractures, one fracture or several fractures, simple geometries of fractures, because when you have a great high density of fractures, you have the problem of creating a mesh, building a conform mesh. And this was the problem I started to work on when I was here at Laboratoire de Mécanique solide and Jaques DESRUES with Mehdi. So at that time I started to solve this problem. So there are two cases. Or we have already the fractures. This figure is supposed to represent a fractured granite. We know already where are the fractures. And the question is to create a mesh, a conform mesh, and to detect in this mesh the lines corresponding to initial fractures. And for these lines, split the nodes to create joint elements, 4 node joint elements with all possible intersections and so on, and to assign this constitutive parameter model to the joint elements. And when you have accomplished that, you are able to apply the load on your model and to have the formations and so on. There is no more real difficulty. The other situation is when you don't know, there are no fractures, but you want to make possible propagation, fracture or crack propagation in some given locations. For instance, here we have a polycrystalline salt. Each color is supposed to represent a different orientation of the crystal, and we want to model the cracking at the grain boundaries. And so in this case, we have to place joint elements on the grain boundaries, and this enables us to model cracks on the grain boundaries. And if we want to go further and to model also cracks penetrating the grains, intergranular cracking, we can also place joint elements inside the grains, so on the sides of all surface elements, triangles here. And so we will able to simulate propagation also inside the grains. So I call this method, which consists of enriching the classical finite element method with joint elements that we can place everywhere where potentially the crack can propagate and so on, and with adequate appropriate constitutive models. I call it joint enriched finite element method, GFM, which is now available in the code research I have developed and I will be using for the simulation I will present here. And we see that it is a very efficient method. In this method, all the difficulties related to the presence of cracks and fractures and so on are solved initially at when we are creating the mesh. And when the conform mesh, appropriate mesh is created, we can forget that there are complexities like cracks and so on, and we will see that in the simulations and we present to you. So now, let me talk about the constitutive model, cohesive zone model. Cohesive zone models have been proposed initially for metal alloys as an alternative to linear elastic fracture mechanics, or fracture mechanics, which is based on the concept of stress intensity factor and tenacity and so on, and toughness and so on. And it is an alternative method which considers that there is not a crack tip well defined, but it is the zone around the crack tip in which some irreversible phenomena, high plastic deformation and so on are happening, and gradually the material loses its cohesion. So it is a gradual debonding which defines finally the crack, which is progressive. So there is a cohesive zone, in which zone around the crack tip you have a relation between the opening of the fracture, here UN, it is positive for tensile, for opening, and the stress, the tensile stress applied on the interface. There is a traction separation law, which defines the mechanical behavior of this interface. And when we arrive at this point, we have a well-defined crack. This concept is really very appropriate for rock-type materials, this debonding, gradual debonding, because it is observed at different scales. We studied cracking of some rocks and their freeze-thaw cycles. It was the PhD thesis of my boss. And we looked carefully at the extremity of the fracture, represented here. There is not really a fracture tip, but there is a zone in which, if we look more closely, we see that there are rock bridges, different densities of rock bridges. Their density is increasing. The density is the surface of the rock bridge related to the total surface, is increasing when we go to the intact material, and decreases for the crack in the cracked part. Also, at a greater scale, when we look on the joint on the surface, on the starting points or departments of rock falls, here we have a start point of a rockfall in Alps, in south of France. To have the scale of this photo, you can consider the man is one of our colleagues who is inspecting this, and geologist who is inspecting this point of departing of rockfall here. And geologists have observed that the weathering of rock joints, which leads finally to this instability of rockfall, the weathering consists to reduce the surface of rock bridges. So the surface of rock bridges reduces with weathering, and when it is sufficiently small proportion of rock bridges, a triggering action can create instability on the rockfall, and so the last remaining parts of rock bridges are broken or damaged or broken. And so in this problem, we see that we have two modes of this damage, of failure of rupture of rock bridges. In mode 1 for this surface, subvertical surface, and in mode 2 or shear for this part of inclined surface. And so our cohesive zone model has to represent these two possibilities of damage. So we built a damage, a cohesive zone model about 10 years ago with one of my PhD students to represent this damage in rock joints, which transforms finally at the end of the damage process the intact rock joint, the initial rock joint, to finally a fracture. And we have here the strength criterion of this interface rock joint in the shear stress versus normal stress plane. So the positive sigma n corresponds to tensile, and negative on the left to compressive strength, to compressive stresses. So initially we have this strength surface, which is characterized by a tensile strength sigma r, by a cohesion C, and a friction angle phi 0. And the damage process consists in degradation of this surface to another one. This is the residual strength domain, which has corresponding to fracture. So a 0 tensile strength, a 0 cohesion, but a friction angle, a residual friction angle. And all this evolution from the initial to the final surface is included in this expression of the strength criterion, depending on the parameter, damage parameter D, which varies from 0 for intact state to 1. And the relation between the stress vector and the displacement, relative displacement of the two sides of the interface. There is a normal component and a shear component is given by this relation. We have the stiffness tensor K affected by 1 minus D for the damage process. And there is also a parameter beta, which controls the transition from ductile to brittle character of this behavior. So we have here the traction separation law represented by this curve, elastic parts, and maybe we can have a peak stress and then the weakening part, and it can be very brittle for small values of beta, or more ductile for greater values of beta. So this is the strength. Now the elasticity relation is a real more complex, because we must take into to be able to model the following. When the damage variable is equal to 1, so we have the fracture. If there is no more stiffness, we cannot prevent interpenetration of the two sides if there is a compression. So we must have a residual stress in order to make possible a unilateral contact. So we have a residual stress, no linear elastic relation. We have sigma n is related non-linearly to un opening, and if un in negative values for compression or closure is limited to a value E, because for this value we have a compression, infinite compression, which would be needed to obtain this closure. And so we have this no linear elastic curve, which is the black curve given by this relation, that for damage transform is this to this red line. This is the traction separation law I showed you now. And for the final stage of residual stress, when d equal 1, we have this part, and this part corresponds to the blue line. We have unilateral contact because a parameter of a parameter S is 0, so there is no stress if we have opening, if S is 0, if UN is positive, and S is equal to 1 if there is compression. All of these complexities are really necessary to be able to model what we want to model. Okay, and the next complexity we have to introduce in the model is the plastic deformation. So the constitutive model is also enriched with plasticity. It is because when you have a great amount of slip, so you have it is irreversible, and so we have to represent it with plastic strain in the model. So all of these have been introduced in the model I call CZ-FRAC, so this cohesive zone fracture model, which I will be using in the next. And so we see that we have no linear elasticity, we have damage, we have unilateral contact, we have plasticity, and all of these no linearities are make very challenging the algorithm to write for numerical iterations and so on to converge. Okay. So this was tested for some experiments, experimental data we found in the literature. For instance, here we have a sample with 2 notches here, and we apply a traction on the sample, cyclic load unloading, and we have here in green, we have in red the experimental results we found in the literature, and we were able to determine the parameters to find to fit well this behavior for normal mode 1 crack propagation, and also in other configuration here for mode 2 crack propagation. Also, we compare the results of these cohesive zone models to what is given by linear elastic fracture mechanics in some typical cases where they can be compared, and we can verify that if we have some appropriate corresponding relations between the parameters of the two models. So linear fracture mechanics is based on toughness, and there are some relation between this parameter and parameters of the model, and we can find a perfect agreement between the two type of results. Also, it is interesting to see that because of the weakening behavior we have some instabilities. For instance, here we have on this sample, we apply this displacement, looking the displacement on the other parts. And displacement creates a shear, and we measure the force F, and we see that the force displacement curve has some instabilities. So we have in some instance we have a sudden drop of the force, and this instability, which is similar to the phenomenon of stick slip, which is well represented here, is very useful to model instabilities due to leading to induced seismicity. And we will see some example of this later. Okay, so just also one word about the effect of the fluid pressure. So just our constitutive model, we introduced the effect of the fluid pressure by replacing, as for porous materials, the total stress sigma by an effective stress. Effective stress is defined by the effect of pressure, which acts only on the normal component. And also here, the pressure, if we have a fluid pressure, the fluid pressure cannot be applied on all the surface because there are parts of the surface, contact surface, which are occupied by rock bridges. So we have a reduction coefficient BF, which is like the Biot coefficient for porous materials. And this this coefficient would be related to the damage parameter D, but it is more complicated because even for the totally damaged fracture, D equal 1, but because of the rugosity of surface which are in contact with the deformation of this interface, the part of the surface which is elevatable to the pressure to pressure be applied and make a mechanical effect is varied. So it is really for me an open problem. I have not really the solution to what value of B we must take into account, and it is important because because very often we have closed fractures. The fractures are closed, but there is a fluid pressure. So what is the effect of this fluid pressure? It is absolutely different from the case of the fracture is open and filled with water. The situation was very different because these contact surfaces, but I have not really the solution for this. So it is an open problem. So now let's go to some example of applications of this hydromechanical models. The first application I will present to you is natural fracturing in sedimentary basins. We studied in a PhD thesis with IFP Énergie Nouvelle some years ago. The problem is that in some cases of geological overburden formation, we see that some vertical fractures exist, and the explanation given by geologists is that there must have been some periods of rapid fast sedimentation, and so a very rapid increase of the pressure in the reservoir. And if the sealing formations have a small permeability, the overpressure cannot be dissipated by diffusion in the porous rock, and so there would be a breakthrough of the overburden to dissipate this pressure, and this explains the origin of this vertical fracture. So we try to model this phenomenon with these tools I presented here. This is a two-way coupling, hydraulic towards mechanic, and also mechanics to hydraulic, because the opening of the fractures in this simulation changed their conductivity, and it is determinant for the competition between the fractures which will appear here. We have here the what happens? I don't know why you cannot see. I don't know why you cannot see the simulation. Okay. Okay. I think it's not the same thing for other. Yes. Okay. So you have this competition between the fractures. When one fracture grows, it drains the fluid pressure around it, and the fluid around it, and decreases the pressure in its surrounding, and prevents other fractures to grow. It is like a competition between trees. And so here we have a real two-way coupling, and this leads to some correlation between the length of the fractures and their spacing, this correlation which has been well observed in field observations. The next example is related to fracture propagation around deep galleries for nuclear waste disposal. It is the topic of an ongoing PhD we have with Andra. So the question is that, the problem is that when the galleries are created, some fractures can appear. So there is an EDZ, excavation damage zone around the galleries, in which some fractures exist, and the question is if the increase of pressure in the gallery can first open the existing fractures and also make them propagate. And so to analyze this problem, we created the geometry of this gallery with the different type of fractures around it, and we applied the at the first time, beginning, just the fluid pressure, so no gas, but just the incompressible fluid pressure on the wall of the gallery, and it penetrates the fracture and also the porous rock around. And so here is the question is what BF coefficient B for the fracture must be applied in the initial state, and the results are really depending on this coefficient. It is why I said that the value of this coefficient for close fracture is important, and really I have no response to this question. So I tried some values, and we can see here the results for the pressure evolution. So we consider a case where there exists also 4 shear fractures around the gallery. And we see here the evolution of the pressure and the opening of the fractures and then the propagation. In the following simulation, it is the same one, but you see the vertical stress. So you see the stress concentration, which is propagating with the crack tip must be near here. The next one, it is the damage variable D of the joint elements. And what it is interesting to see here that initially we have a configuration which is perfectly symmetric, has 2 axes of symmetry, vertical symmetry and horizontal symmetry. But at the end, we maintain the left-right symmetry, but the symmetry between the top and the bottom fractures is lost. And it is because of interaction between the fractures. When one fracture here in the bottom, for example, propagates, it decreases, it relaxes the stresses for the top fracture. So it is a negative, it is the competition between them. But when a fracture propagates on the right, it does not decrease the stress on the left, and maybe it increases it, even increases it. So the 2 fractures can propagate without competition, and also the symmetry is maintained. Okay, so the last application I will present to you is related to wastewater injection in a reservoir in a site called Timpson, well known, in Texas, USA. He's a PhD student, Danilo Zeppili, from University of Rowan University in New Jersey, who studied it and used this work to do the simulations. So there are some, this is a site which is very, very well documented from geophysical and geological studies and so on. And we have an idea of the fault geometry. So Danilo prepared the model for all the layers constituting this reservoir, this geological site and the geometry of the fault. And there are 2 wells, south well and north well, and south well is located here. And Danilo determined
carefully all the parameters, permeability and mechanical properties of all the layers from the available data in the literature, and he considered always that for the fault we have the same properties of the layer by reduced by a factor of 10 for cohesion and friction angle and so on. This was the only hypothesis in the model. And then, so we have the well here, and the fluid is injected here. Danilo also tried to respect carefully the history of the pressure injection in the reservoir. It was not pressure, but it was injection debit. Simulated exactly with the same debit. And we see there first the pressure increase in the reservoir, and the fault is impervious, so the flow cannot cross it, and we have increase of pressure on one side of the fault. In this example, we see the evolution of the stress, and we see a sudden change in the, yes, here we see a sudden change here, and this is the instability which happens, and we can understand it better here. It happens 2,000 years, 1,000 days after the starting day of the injection, and it is a seismic event corresponding to a 6 millimeter slip, sudden slip on the fault, which is also related to sudden change of stress field. I showed you, and so in this simulation we were able to determine the displacement, also the stress drop, and also the occurrence time of this instability, which corresponded well to a well observed seismic event at around this time, this period, this interval time after starting injection. But the determination of the seismic magnitude from these results needs more theoretical investigation based on energy balance approach, because there are some geophysical models giving the magnitude of seism to the energy, but which energy to consider here, it is we are working on it. Also, we were able only to simulate a first event, and not there are a series of events, because when for the first time damage happened on the fault, we have a planar system, and so when damage is triggered, it is spread out all along the fault, and so all is damaged, and there is no room to other successive damage periods, events, and so on. And so if we want to have successive seismic events, there are different solutions. First, maybe to consider not a planar system, planar fault, but take into account the curvature of the surface of the fault. We tried it, but the result was not really very convincing. The other solution is to introduce in the cohesive zone model the healing process, because the healing process is the process that makes when we have damage on the fault after some time due to some physico-chemical mechanical problems, the fault can recover its initial cohesion and so on. And so it is not, this process is not included in the core cohesive zone. So to conclude, finite element method enriched with joint elements, what I call GFM, and with appropriate cohesive zone models, appropriate constitutive models for joint elements, really provides an efficient tool for fracture propagation and fault activation and crack propagation in materials and so on. I presented some applications to nuclear waste disposal, water waste storage, CO2 sequestration, and geothermal production have also been studied, modeled with these tools. in perspective, we need some improvements to introduce unsaturated fracture and matrix. Unsaturated because we must be able to inject a mixture of water and gas. We are working on this. And also the mechanical effect of pressure, which is needs more investigation, theoretical also, maybe also experimental investigation. And the healing process, which needs also to be introduced for some applications in the model. And in perspective of applications, we have a project of model the problems related to hydrogen storage in salt caverns. So the thermal cracking in the wall of the salt caverns because the difference of the temperature of hydrogen and the natural temperature of the rock formations. So this hydrogen storage in salt caverns, it is a project we have with Emerite, and we are consulting for a new future. So I finish my presentation here, and coming back to the heritage of Pierre Berès for me and the impact of his work on my professional life, I can say that. So I started 37 years ago my research career with Pierre Berès and with salt caverns, and I discovered salt caverns with him. And now, 37 years after, I finished my presentation here with salt caverns. And so it shows that when you fall in love with salt caverns, it is like you fall in the salt caverns and you cannot go out.
I have a question about the application of the nuclear waste disposal.
Yes.
What is the constitutive equation, the constitutive model that you use for the claystone, for the material? Did you use a particular constitutive equation?
For the matrix here, for this application, the elasticity is sufficient.
Okay.
Yes.
And about the hydromechanical coupling that you show, did you implement also the effect of permeability and also the evaluation of the permeability with the fracture opening into your model?
Yes, so when I said the elasticity is sufficient, I must say the pore elasticity. So the matrix is pore elastic material in this application. And yes, we did a lot of simulations. Yes, I think, so we are able to take into account the variation of the conductivity of the fracture according to the cubic law.
Yeah.
Yes, so we are able to take into account this coupling, so this variation with the opening of the fracture.
Okay, thank you.
Mehdi?
So, you know, Pierre Berès, in the introduction of his PhD thesis, he had said that analytical solution is has a very eloquent expressiveness. La solution analytique, c'est une expressivité éloquente. You showed that numerical computation is also very eloquent.
Thank you very much.
I wanted to ask you whether you have shown that for the, I think if I understood well, I'm not quite sure, for the initiation and propagation of fracture, you use something like a Coulomb criterion. I wanted to ask whether you use the energy concept or not, because I understood that because of the singularity of stress, mostly in fracture mechanics, everything is based on energy concept and tenacity factors and something like that. What do you do with this concept?
Yes, so this is a good question because there are two cases. when we have the fault activation, we have an interface, and there is no really stress concentration. And the relation I presented to you, which was we have a sigma r, tensile stress and cohesion, is really sufficient. But when we have fracture propagation, there is at the end of the fracture a stress concentration, and we discovered that there are two ways. Or for the fracture tip, what happens in the fracture, we can define a length of the process zone. It is the length of the zone in which there are irreversible processes and so on, which determine the propagation. If the length, or mesh size, the length of the joint element is enough small compared to this process zone length, so we have nothing to modify, and our model works well. I showed the comparison with linear elastic fracture mechanics. But this process zone is very small, and we cannot, for our applications, to consider mesh sizes even smaller than that. And so we consider greater size of the mesh, length of the mesh and joint element. But what we can do, based on some analytical, from some analysis of the stress profile around the crack tip, fracture tip, we change the parameter of the joint element with its size, L here. So, and it works very well. So if we change the strength, the tensile strength and cohesion of the joint element with the size of the element, we can remove about 90% of the mesh dependence.
The Earth is a dynamic planet, and in the context of underground storage and geoenergy, any storage extraction or injection could induce deformation at short or long term. And if you want to predict the evolution, it's interesting to understand the mechanism of deformation. So at short term, demands, laboratory experiments are pertinent. At long term, field experiments are interesting, and Pierre developed very innovative approaches. With Pierre, we were co-chair of a national program gathering Mécanique and geologists. And Pierre was interested by the idea that analysis of natural deformation could help understand long-term induced deformation. So I will talk about the mechanics of the upper crust, but from the point of view of a geologist. So what we see? First, we see that there are earthquakes in the upper crust, and this brittle mechanism, which is controlled by friction, leaves the place to a ductile plastic deformation in the lower crust. When we plot the differential stress versus the depth, it is the famous Christmas tree. The problem is that this model is not compatible with geological observation. When we look at the geological observation, we see that in the upper crust, there are a lot of ductile processes. There are folds, there are creeping faults. And so the first question is, what is the mechanism of ductile behavior in the upper crust? Moreover, it's sometimes possible to see that faults develop in the same time as faults. And so it's interesting to discuss also how ductile and brittle deformation interact and evolve in the crustal deformation. So I will say that the mechanism of ductile deformation is pressure solution. It is also a sealing processes. I will talk first of the observation in the nature, then about experimental approach, and finally of some modeling of pressure solution. First, the observation. I will present 3 examples. One with the flexural slip fault, one with fault with axial plate cleavage without any fault, and shear zone along fault. For the 2 fault, I will discuss on the cross section of the Alps. The outcrop are along the line here, but I add this zone, which is this sedimentary cover, which is the sedimentary cover at the time of the deformation, so that you can see the depth of the deformation. So the first marker is pitted pebble. Pitted pebble is 2 limestone like that are pressed together by stress, and they dissolve here, and you see this pitted pebble, and they are always associated with fracture. And the dissolution, the matter which is dissolved, is most often co-deposited in the fracture. Another marker of deformation in this flexural fault is a tectonic stalolite. Tectonic stalolite develop at relatively low depths. You see here it is a dissolution, so you see on the element map that the calcite disappears completely, and aluminium and silicium are passively concentrated because they are insoluble minerals that are some rare phyllosilica. It is a transgranular dissolution. The rock is mostly monomineralic, with mostly soluble grain, paradoxically, and the grains are of various size. The dissolution could be, the fracture could be perpendicular to the stalolite. In this case, it accommodates flattening. You may find sometimes stalolites that are in the prolongation of the vein. So in this case, it accommodates folding. And finally, it is also interesting to see how pressure solution can accommodate sliding along the fault or along the strata. So it works like this. When 2 pieces of block are blocked together, if there is dissolution on the asperities that oppose the displacement, that's what you say in geology, stagolite. If you have this dissolution, then the block can displace by aseismic sliding. And the part which is dissolved is redeposited in the vein. So after the block is eroded, you see the vein here, and here the slag arrive. So it is completely aseismic deformation by pressure solution on fault. So thus limestone may deform by flattening, rotation, sliding with a multigrain microblock. That's the example on the top. You can accommodate very large deformation. This is a real fault in the Alps with a shortening of 50%. Geological deformation about 10 to the minus 15, something like that. But the deformation at the scale of the rock is not very important. And most often there is no change of strata thickness. So, because there is no change of strata thickness, it is possible to unfold the fault. This was proposed a long time ago by a polytechnician, Jean Gogel, who wrote a famous book on the mechanic of the crust. So, how we test the compatibility of fold and fault? So we can consider a zone like this with several folds and faults. It is possible to unfold by 2 methods. First method is to unfold here by describing the surface as a coordinate network of rigid triangle. Each triangle is laid flat and automatically base fitted. Or it is also possible to describe the surface directly as a 3D developable mesh, and then the developable mesh is directly laid flat. With this, it is possible by comparing the initial restored state with the initial, it is possible to calculate the finite displacement. And then, if you do this, for example, for the wall transverse range, and then you compare this direction of displacement with the slip vector of earthquake, that is a very good coherence. So the fall and the fault, including the earthquake, are clearly compatible and associated. So to finish this part of flexural slip fault, it is monomineralic rock, mostly soluble grain, limestone, sandstone, dolostone. Dissolution deposition occur around microblock with fracture, so possibly linked with seismic process. There is only minor deformation, but thanks to the stratification, you may have very large deformation. So now I will talk about the next type of fault, which is a fault with accidental plane cleavage without any fault. In this case, you have two markers. First, space cleavage. Space cleavage developed in this type of rock. It is a polymineralic rock with soluble and insoluble grain. Soluble, calcite, quartz, dolomite, feldspar. Insoluble, mica, chlorite, and iron and titanium oxide. So in this case, you see here the same concentration of aluminium and the same disappearance of calcium here. If you are able to calculate, to establish this evolution of the content of aluminium, it is possible to calculate the shortening. And it is rather like you see here. And this leads to tectonic layering. So you have a layering that develops with this type of deformation, with relatively small deformation. The layering is constrained either by initial block or by the fold. Another type of cleavage is a slaty cleavage. This is completely different. In this case, you have very large deformation that is attested by truncated belemnite or microfolding, and you have elongation of 100 to 300%, and you have shortening of 50 to 60, 75%. The duration is about 10 million years. So it is the same type of rock, but when you look at a BSD image, you see that the calcite, that the grains are very, very small. You see, for example, the median part is about 2.5 micron. So it's very, very fine grain. And when we look at the mean shape of the grain, they are almost equal. So if we compare the mean shape with the strain ellipse, it is clear that you need to have a grain boundary sliding in order to accommodate this very large deformation that look like grain boundary, that look like what HB and Veral say as a superplastic deformation. It works like this. You have dissolution in the dark blue and precipitation here, and then you transform the rock like this. So it's a ductile deformation without any fault or internal deformation, because when we look at the LBSD image, we can see that there is absolutely no plastic deformation in the grain. Now that's the other deformation for fault with axial plane cleavage. So in this case, it is polymineralic rock, fine soluble and insoluble grain, as marl, shale, slate, schist, large ductile deformation that is of the type of superplastic flow, with the development of tectonic layering, and of course with large deformation of here 60% of shortening. Now I will talk about the shear zone along the fault. I will show only one example. It is a North Anatolian fault with a displacement of 80 kilometers. In this zone, you have two types of rock. The rock here that are in the locked zone, meaning the zone in which the earthquake initiates, but once the earthquake is initiated, the zone do not deform too much. And another zone here, which show creeping in the interseismic period. So we measure the deformation in each zone, and in the locked zone, we find mostly stellarite and vein, but when we calculate the strain ellipse, it is not very large. 1.3 with a shear strength of 1.2. So mostly it is the displacement is accommodated by the earthquake. On the contrary, in the creeping zone, you have a large creeping zone of several kilometer width in which we can calculate the deformation, and we find the strain ratio of the strain ellipse of more than 8 with a shear strength of 2.7, and this is accommodated by grain boundary sliding. And in some zone, you may have some cleavage that are almost parallel to the shear zone. So in this case, the shear strength was estimated to be about 100. So if we look at the zone which is creeping, you see two types of rock: the gouge that show very large deformation, and the damaged zone that show less deformation. It is possible to cumulate all this zone here to calculate the total of the gouge, the total of the damaged zone with limited deformation, and it is possible to calculate the displacement that are being accommodated by the creep, and it is half of the 80 kilometers. So in this case, in the shear zone, we find once again the same difference between the rocks that are mostly soluble with various grain, various size of grain, and the rocks that are a mix of soluble and insoluble, but with very fine grain. In this case, it is limestone, sandstone, dolostone, alternatively marl, shale, slate schist, volcanic ash in the case of Turkey, and gouge. In this case, you have minor internal deformation, so mostly seismic sliding. Here, you have large internal deformation by pressure solution, mostly aseismic. So now we consider the new model of the strength versus depth, where we must add a part here, which is pressure solution. But you see that it is a relatively large part, so this part is constrained by the effect of the grain solubility, the effect of the grain contact, and the effect of the grain size. So to discuss this, I will pass to the next part, which is experimental approach of pressure solution. In this experimental approach, on the left, so you see a cylindrical indenter that is indenting a soluble mineral in presence of a solution. The blue is a free solution. The red is the trapped solution that must stay under stress and that must allow fast diffusion. The chemical potential which is induced is equal to the difference, is proportional to the difference between the normal stress and the fluid pressure. There are sometimes some other stress driving force, but they remain negligible, at least for what we have to say today. Talking about stress driving force, I must also talk about the force of crystallization. The force of crystallization, it is if the fluid solid activity corresponding to a pressure P is superior to the solid activity of the solid at the contact, then you generate a growth, a crystallization, with a force of crystallization that can uplift the indenter. This is well known, that for the crystallization of halite, for example, then can damage monuments. And also, it was one of our favorite topics of discussion with Janos. So I will show an example of force of crystallization in nature. So now, after the stress driving force, we must talk about the limiting process, as it is a dissolution, diffusion, and precipitation. There are three processes in series, and if one is much slower than the other, it limits the total. So it could be the diffusion, and in this case, the displacement rate is proportional to the transfer, the diffusion and the thickness of the trapped field was, the solubility, the stress, with an exponent I will discuss later, and inversely proportional to the distance of transfer. On the contrary, if it is the reaction limited, it is proportional to the kinetics of the reaction, the solubility, and the stress. If we want to differentiate these two types of reaction, of creep law, The solubility has the same effect. It is a good news because we can accelerate if necessary because it is very slow. There is a difference in activation energy and in orientation of the crystal because the kinetics and the diffusion has not the same effect on this. And then there is an effect on the distance of mass transfer. And finally, about the trapped fluid phase, there are two models. One model which considers that it is a trapped fluid phase that is not supposed to have some exchange with free fluid, and another model, island and channel structure, which is we may have some exchange. So now I will show you some experiments. The first one is by Hickman and Evans, and they test the difference between soluble and insoluble contact and soluble-soluble contact. They do this under a microscope. For example, they test halite against halite, and in this case, they find absolutely no deformation. So when you have two soluble species, nothing happens in their experiment. When they put silica against halite, the deformation was much better. And when they add clay mineral, the deformation was even more important. So this means that, why this difference? This is probably because when you have two soluble minerals, they can heal together, and then the diffusion is much more difficult than when you have soluble and insoluble contact that are less sealed. I want to show you that when you have two contacts, insoluble-soluble, sometimes you may have a small deformation. I show this example, so it is in hydrothermal condition with more than 300 degrees, duration of more near 50 days. The fluid is activated the solubility, and it is quartz-quartz in aggregate. And what we see here, it's at the contact between the grain, some microstylolite that develop. And the microstylolite we see here, they are rooted on the dislocation where there is a maximum of strain energy. So this modifies the shape of the surface, but surface energy counterbalance this modification. So there is an equilibrium between the effect of the dissolution rooted on the dislocation and the surface energy. But anyways, what is important, there is a small deformation, always. Now, let's see some example of soluble-insoluble contact. So in this case, it's much better, it's much faster. It is almost the same deformation, hydrothermal deformation, quartz metal. The indenture diameter, we test 201 millimeter, but only the 200 give some result. And here we measure the deformation at the displacement at the end of the experiment. And I plot here the displacement versus stress. You see that it is rather dispersed, but there are various types of conditions, natural or synthetic. Sometimes in some we fill the cell first, and then we put the indenture on the sample. Other time we first put under stress and then fill to see if the fluid can go through the contact. And then we test also various orientation of the crystal to see if to differentiate between diffusion and reaction rate. And what we see first the driving force. It is an exponential relation, but the exponential relation here is mostly because we are at very high temperature, below some tens megapascal. It's not necessarily exponential. The deformation is limited by the diffusion because there is no effect of the crystal orientation, no effect of the quartz type, and no indenting for the large indenter. Finally, the island and channel interface is, in this case, a good model because when we put under stress the sample, it was possible for the fluid to go through the internal interface. So there are some exchange between the interface and the free fluid under stress. Moreover, you see that the roughness of the contact is very, very various. And this explains why you see there is a large dispersion of the value in pressure solution. This is always the case with indenter because the contact, the structure of the contact is very important. So I want also to talk about the effect of the change of stress. So in this case it is in indenting. Here in indenting where we change we made a static change of the stress, or a dynamic loading when you let the ball fall on the indenter. In all cases, you see that you have first a nonlinear evolution, which is a power law in all cases, and sometime after sometime long time, you may have a linear evolution. There are several explanations, but one explanation could be that when you change the stress, you develop some microcrack, and then it needs some time for the microcrack to heal and to reach an equilibrium. I will show you also another effect, an effect of the fracturing on another example. It was indenting of halite. You see that during 70 days nothing happened, it was linear, and then suddenly the deformation accelerates incredibly. Why is this? Because this day I made a mistake and I put a bit of shock on the indenter, and I create some fracture which are radial fracture. And the explanation is the following. Before the fracturation, the diffusion has to occur along the radius. Here, because the fracture are filled with free fluid in which the diffusion is very fast, the only part where the diffusion is slow is these two parts, these four parts, and then the distance of mass transfer with difficult diffusion, if you can say, are much smaller. And so in this case, you accelerate the deformation. Most often, we did not see this in the experiment, but in nature, probably the fracture could see, but it could take time. It could take time. You see, after 150, after 70 days, we did not observe the thing. A last experiment is experiment with a flow-through experiment in porous rock by Zhang and Al from the Utrecht team. In this case, they made flow-through and deform porous rock, and they find that if they use saline solution or pure solution, the deformation is limited by diffusion. However, when they inject some solution with phosphate or magnesium, then they reduce drastically the deformation. So in this case, the deformation was controlled by the reaction. So if I summarize the result of the experiment, we have a viscous process, a creep law, an effect of stress which is exponential but probably linear in natural deformation, two types of limiting process. If it is diffusion, dynamic, the channel and the island structure is probably evolving. We have a crucial effect of the nature of the contact. The diffusion along insoluble contact is always much faster than the diffusion along soluble contact. And finally, there are a crucial effect of fracture and microfracture, fractures that increase the strain rate, but healing after some time will reduce this effect. So I will finish by the last part, which is the modeling of pressure solution in natural deformation. I will first model the deformation of the polymineral rock with fine grain, soluble and insoluble, and the form, it is the one on this part with a large deformation. And the first question is, what is a creep law? So the creep law, it is in the alpine deformation. The creep law is very, very influenced by the grain size. You see, only the shale with very, very small grain can deform with a large deformation. On the contrary, near this shale, you have, for example, granitoid, and in the granitoid, which are a mix of soluble and insoluble species, they have a grain size of 50 to 100 micron, and they show no ductile deformation, mostly fracturing. So pressure solution is very sensitive to the grain size, at least, you see. So we use the diffusion limited creep law by superplastic flow. The only parameters that we don't know is these parameters that have been estimated by experiment by two teams in Grenoble and in Utrecht. And we find almost the same order of magnitude, 10 to the minus 19. So we use this value to draw deformation map with stress, grain size, and the line are the strain rate. You see on the top the zone red, which is the zone of experiment, and the line, the deformation, correspond to a deformation of 10 to the minus 9. Now, there is a problem with the deformation in nature. Because in nature, the deformation is 10 to the minus 14. And then, if you look at this, you see that with this map, theoretically, with 200 micron, you must have deformation. And it is not the case. We have seen that we have absolutely no deformation with 200 micron. So, why is this discrepancy? We propose that at high stress, the coefficient dW is relatively high, no problem. But at very low stress, it could be much smaller. Why is this difference? Because at high stress, you induce some subcritical microcrack, and at low stress, you develop almost no microcrack. So we use this to put a correct factor that puts the value of 10 to the minus 15 for the experiment, keeping this, of course, and for the fold, what we say a fold creep, we use this value here, and between linear evolution. So with this, we are compatible with experiment and fold creep, and we are compatible with fold creep. You can see that if you want to apply this to underground storage, you see that with this type of deformation map, you may have, for example, a differential stress of about 1 to 10, you have a relatively important deformation, 40% a year. So it is significant. Now, what happens when you have polymineralic rock, either with large grain, or when you polymineralic rock or monomineralic rock, large grain in case of Soccer fault with stylolite, you see the stylolite, and the North Anatolian fault with mostly limestone. In this case, you see that if you take the grain size of several millimeters, when you reach fault zone of 10 to the minus 12, you will have a large value of stress, and it is likely that at this value you will create some fracturation. The fracturation will activate the deformation, but it will be only transitory. So if pressure solution cannot accommodate the imposed loading rate, earthquake fracturing occur, and this induces a non-linear post-seismic displacement due to the fault healing. So we can discuss now this fault healing, because pressure solution is both a creep and a sealing process. So the first mechanism that seals the rock is the surface energy minimization. If you have very thin fracture of submicron, then in this case, you have progressively the transformation of a continuous surface to a cloud of fluid inclusion in order to minimize the surface energy. That's rather fast, but that concerns only a very, very small number of cracks. Another possibility is fluid flow coming from depth that with free-phase dissolution or coming from the cleavage. Talking about fluid flow, it is the opportunity to talk about the force of crystallization, and I will show you the example of force of crystallization. This example is in Utah in the context of the large vein, travertine, and you see the vein show the younger calcite is at the base, and the older calcite is at the top. We did this with the uranium-thorium method. How it works? This is if you have a flow of fluid with CO2 in it, you may reach a depth where there is degazing. If there is degazing, the concentration of calcite in the fluid change, and it precipitates. And then you have precipitation at the contact between the zone, the rock, and the fracture, and you can uplift, in this case, about 10 to 20 meters of rock. So it offers us to calculate the delta P, and also the rate of sealing, which is 0.3 millimeter by year, which is rather significant. Now, the last marker of crack sealing is the association of solution cleavage of stallolite and vein. In this case, you see that when you have such evolution, the distance of mass transfer increases when the vein is filled. And this leads to an exponential decrease of the porosity and of the permeability. So if you assume that the permeability is just the ratio between between the time and the characteristic time, which is characteristic of the rock, for example, calcite in the upper part, quartz in the lower part. In this case, using this, it is possible to calculate the evolution of the fluid pressure by a model injecting fluid flow at the base, starting from near hydrostatic pressure and progressively getting the lithostatic pressure. If you have both the strengthening due to fault healing plus an increase of the fluid pressure, this will facilitate new earthquake. And in this case, pressure solution and healing are crucial processes during this interseismic period. And in the context of underground storage and geoenergy, probably it's necessary to think about that. In any case of input, output, mass transfer, deposition, dissolution, and depth, this could modify the earthquake cycle. So, as a conclusion, first pressure solution work only if you have mobile mineral. So I talk mostly about calcite, dolomite, quartz, feldspar, but there is also halite, gypsum, and this solution must be here, of course. In this case, when you have fine grain with a mix of soluble and insoluble, as marl, shale, slate, schist, volcanic ash, gouge, the pressure solution is easy and fast. You have a real ductile deformation, a kind of superplastic behavior. And in this case, the differential stress is here. It is very easy, very low stress. If you apply to man-induced deformation with a differential stress of some megapascal, you may have relatively important deformation during 1 year. In parallel, you have the other possibility when you have large grain with soluble and insoluble, or mostly soluble grain of any size, in this case, as the limestone, sandstone, dolostone, and granitoid. In this case, pressure solution is rather slow, and the deformation is partly ductile and partly brittle. You have a non-linear evolution due to the healing of the fault, and you have also fluid flows that are transitory. And in this case, the zone is here, very near the brittle deformation. In this case, you may have a lot of fluid input and output in the zone, and if you want to test some mal-induced deformation, the key anyway will be the evolution of the rock, mainly strengthening and softening and development of layering and something like that could occur during the deformation and transform the rock. I did not talk a lot about that. Now I want to put only 2 key points to develop. First, I think it could be interesting to continue developing calcite datation because it could help evaluate the sealing, but also the creep. And it's also very important to understand why we have this difference between soluble-soluble contact and insoluble-soluble contact, and why or how we have this effect of stress during that change the value of the diffusion along the contact. That's all.
Is there some questions?
So Jean-Pierre, it's a beautiful talk, and I think one thing we have for many years agreed on is that pressure solution is probably the most important deformation mechanism in the crust, right?
In the upper.
And truncation of the profile is something that has come up often in the work of both our groups. So of course I love it. So I only had one little reservation because it relates to a talk I gave earlier this week about pressure solution salts, right? So you mentioned the healing of the grain boundaries between light minerals, and of course you're right about it, but can you go back to the slide where you showed the diffusion coefficient 10 to the minus 24 versus 10 to the minus 19 or whatever? Can you just go back to that for a moment?
It's a long way.
Sorry.
No problem. Where?
Oh, that was
here.
Again, this one.
This one.
So what I just like to make the point, right, that we know in salt that pressure solution continues at very low stresses, and the Hickman and Evans experiment is a bit misleading because the geometry of the experiment very much affects the result. So that, in my opinion, the trends in something like halite, which is very plastically deformable very easily, this transition between the disconnected healed grain boundary at low stress and an active grain boundary at high stress is probably not controlled so much by microcracking, but by microscale plastic deformation.
That's a possibility. I said there are several possibilities.
Okay.
No problem.
So I just want to mention
no
because
problem.
everybody
No problem.
the salts.
No problem. I conclude by saying we must work on this. This is probably the most important point.
The stress level at which this transition is important for us to figure out, right? But,
we must look at this and understand this. I am sure we did not understand completely.
No, that's
it was just a way to put the compatibility between the fold, the nature, and the experiment.
No,
so we need
agree.
5 order of magnitude, but if you find another way, no problem.
I agree with you in broader lines, and I think we need to understand the stress level at which surface energy dominates over the effective stress, right?
Okay, so thanks a lot. Very good. Thanks everybody for staying that late. I'm really happy to be here to discuss about how to localize deformation in claystone. And I guess that I'm here because I spent some time here in LMS working with Alex, Michel, but also I had the chance to meet Pierre and to go inside of the mines several times together with Hakim when he was installing the long-term creep devices. So of course it's not the work that I've done all by myself. It's lots of collaboration that I'm going to present today from my PhD up to what I'm doing nowadays. I'm a pure experimentalist, I guess, because I'm constantly in the lab. I'm a lab rat and I'm constantly trying to control everything that is taking place inside of the rock. So when we talk about localization of the deformation, well, at least me, I always think of that paper from Lochner in 1993, where he's been deforming sandstone and he was putting acoustic sensors. And then you can see the fact that at the very beginning of your experiment, you have a big cloud of seismicity, of microseismicity, of course, so micro cracks all around the sample. And then at some point, when you reach a certain stress level, I didn't put the stress strain curve, but what matters is to see how at some point you start to have your cracks that are localizing and then forming a bend like that. So it seems that it's so what he was observing in sandstone is that the process of localization was dominated by crack interaction, which means that at the very beginning your cracks are not seeing each other, and at some point you have so many of them that they start interacting, and then you form your full deformation. What is very nice is that this has been observed in the lab, and it's far from being the only observation, and on intact rocks. I really like that study that was made by Kato and Benzayan in 2021, where they show some evidence of clusterization and declusterization on the field around a fault zone. So what they did is that they looked at the seismicity in California, and they separated they put a grid like on the map, and they look at whether the seismicity is distributed everywhere or whether it's more localized in some cells. So this is what it means here. So when the black line is going up, it means that you have more and more spread of your seismicity in the zone. And at some point, you see that the black line is decreasing, which means that the seismicity is getting closer to the fault. And so they think that it's the localization that could potentially, in that case, so in red you have some earthquake that took place, and so they think that it's a potential way to know when at some point you're going to have your earthquake. So I'm working in the lab, and I told you that I would discuss about clay-rich rocks. So I'm going to discuss about clay-rich rocks. So clay-rich rocks, we've discussed a lot about them. They contain roughly 50% of clay minerals, but they have many other things. I've been working with different clay-rich rocks. So the one from Tournemire, the lab from IRSN, the one from Andra, the Callovo-Oxfordian one, and also a little bit, but I won't show some result from those ones, the one from Monterrey. So this is an example of the Monterrey clay rock. What is amazing about them is that they have a multiscale structure, but also they are anisotropic. So we're going to discuss a lot about anisotropy in this talk. The different approaches that I've been pursuing over the past years have been to work. So I've been working at different scales. So I did my PhD. During my PhD, I've been performing quite a number of triaxial tests that was monitored by acoustics. Unfortunately, we didn't have acoustic emissions, so what we've been looking at was the evolution of elastic wave velocity during the deformation as an indication of the mechanisms that were taking place. But it was really nice, but at some point you need to see what's happening inside of your sample and to understand what are the mechanisms that are truly responsible for the deformation. So then I came here and I've been initiated to the microscale study together with Alex and Michel. And then I started to look a little bit at what was happening at a larger scale. So classically, when we are doing rock mechanics, experimental rock mechanics, we're putting a wonderful sample in a wonderful triaxial cell. We're applying confining pressure, and then we're applying a deviatory stress, and this is what is happening. So you put your sample, you glue some strain gauges on your sample, and then you deform it. So at the beginning, you're closing all of the fractures, then you have an elastic phase, which is more or less linear depending on what you're breaking. And then you start to have some plasticity, potentially fractures that are taking place. And then you reach a maximum. And because you're in the brittle regime, you have a stress drop. In the meantime, if you look at the radial deformation, you see that while you're compacting it, you're also dilating in the radial direction. And you can track the volumetric deformation, which is a combination of the axial and the radial. If you look at the elastic wave velocity evolution during the deformation, what you would expect, because elastic wave velocities are sensitive to the fact that you have voids or not inside of your sample. Meanwhile, the compaction, you have your P wave velocity that is increasing, and then as soon as you start dilating your sample, then you have a decrease in the P wave velocities. This is what we're mostly observing all the time. So if you take samples of clay-rich rocks with two different orientations, one with a horizontal bedding and one with a vertical bedding, you apply different confining pressures, and then what you observe is that you have a classical brittle behavior with stress drop. You have an increase of the maximum stress with confining pressure. All of that is classical, so we're happy. It's good. And then if we look at one of the things that we see is that obviously we have a slight difference in terms of behavior between disorientation and disorientation. Right? Because we see that we have much more plasticity in that case that is taking place. If we look at the evolution of P wave velocities during the deformation with different angles with respect to the bending planes, we will see some very nice things. So for instance here, the light blue that you barely see is the velocity inside of the bending plane. So the maximum velocity inside of your sample. It's the upper one here. And then with the dark blue, it's the one with the maximum angle that we could record during this experiment. So we had high confining pressure, so 80 MPa. And what we see is that actually we have the fastest velocity that is decreasing very early in our experiment. So potentially we have some cracks that are taking place, but also we see that the D3 pass is never dropping. And so it means that along that orientation, and actually it's becoming higher than the other one, so it means that we have a reversal of anisotropy, which means that, okay, we have cracks that are taking place, that are inside of our sample, but obviously we have something else that is taking place. And we see that we have also, in the case of the 0 degree orientation, a completely different behavior. We have some velocities, the green ones, that are inside of the plane in the middle of our sample that are slightly decreasing, so potentially we have some cracks that are opening, and we have the blue ones that tends potentially to increase a little bit. So again, we don't observe the drop in velocity that we were expecting as in a classic sandstone, for instance. So what do we do when you don't know? You look at the microstructure, of course. And so when we looked at the microstructures of our sample, we found those beautiful patterns with along the fracture wall some clay minerals that were fully realigned parallel to the fracture. Also, what we did is that we inverted the Thomson's parameters, which means that what was happening is that we could think that potentially you have some realignment of your clay that is going to initiate the fracture, and which is the reason why. So first you have an anisotropy reversal, and also that explains the whole pattern here. So we observed different mechanisms, and it means that deformation, it's not one single value on a strain gauge. It's a full competition between different mechanisms, and depending on the anisotropy orientation of your sample, you can have you don't necessarily have the same partitioning of the same partitioning of the deformation between the different mechanisms that you could think of. So compaction, crack initiation, and grain rotation, for instance. So because life is more complicated than when we are blind, let's try to see something at the micro scale. So I think that Michel explained extensively what it's possible to do here. So we've done different experiments inside of the SEM on some sample coming from the Callovo-Oxfordian from Andra. So we've been looking at those tiny little samples who are 16 millimeters length and with a flat surface. And then what we did is that we uniaxially loaded them. We waited a little bit, we took a picture, and so on and so on. So when you do that, if I move a little bit, so we've been during those experiments that were lasting 24 hours in a row, 24 hours of fun. So we were taking 12 pictures each time, and then this one it's the full puzzle of it. So this is the first step, and this is at the end. So we didn't go up to failure in that case. So you see that it's moving, and we're going to zoom in order to identify a number of mechanisms. So we observed the compaction, depending on the orientation. You see the compaction that is taking place here. So you're closing all of your cracks. We observed compaction and flexion. I hope that I'm convincing you. We have flexion inside. I'm too close, so I don't see really well. We did observe also some sliding, so you will see some sliding along that fault. And crack. Do you see it, the sliding? So we have some sliding. We observed again sliding directly inside of the clay minerals. And we observed some opening. So we have some opening of here. You see the opening of a tiny little fracture. And again opening. Sorry, but they're pretty. So here you see some opening of your tiny little crack, which means that this kind of method is allowing to, depending on the bedding orientation that you're deforming, is allowing to say. To give an idea of what are the main mechanisms depending on the orientation of the sample that you're deforming. So again, deformation it's much more complex, and it's a great opportunity to have the chance to look at the full field deformation to understand better what is happening and what is really relevant if you want to understand the macroscopic failure. So we did observe, depending on the bedding orientation, so in the case of the 90-degree orientation, the main mechanism is compaction, and at some point you start to open some cracks, and you have a slightly more complex behavior in the case of the 0-degree orientation. But if you go one scale up. So this is a different type of test, but with the camera. So what we did is that we made a tiny little hole. So the diameter of that hole is 0.9 millimeter, and we deformed different sample, and the deformation is tracked with the camera. And so this sample is loaded vertically, and it's a 0 degree orientation. Yep. So the stratification is here, then vertical, and what we see is that very quickly we start to localize the deformation along one bedding plane, and we are opening it, and we have a beautiful fracture that is opened vertically. And if we do the same work on I will try to stop it. And if we do the same work on a 90 degree orientation, so in that case the stratification is horizontal, and you do the exact same experiments, you directly see, you see that you're not seeing what you were expecting. What you see is that surprisingly, you have normally the fracture should be here, and actually we start to see a fracture here. I didn't put the full version where we have the 4 images, but we start to see a fracture here. But at some point, the deformation starts to localize at roughly 30 degrees. And also what we see, and what is very interesting, is that we don't have a continuous fracture that is forming. We have something that is forming a staircase shape. So actually, we do see that deformation mechanisms are much more complex than what we can see, that's what we can think of, and is strongly controlled by the anisotropy of the material. And we see that what would be really nice and really important would be to continue to quantify the different mechanisms and how they then and how it's controlling the way how fracture is propagating. Sorry. So now let's go on the field and try to see if the observations that we've made in the lab by deforming our own sample can be also seen on the field. So let's go in Tournemire, in Larzac, on the plateau, where we have goats everywhere. So there is the underground lab that is located in that clay-rich layer. It's again a clay sample. There, sorry, I didn't show the faults. And so, so you have the main gallery here, and there is a small fault that is present in several places the gallery. So the fault has been drilled during my PhD in that area. And so it's a fault, no surprise. We can potentially try to look at it by looking at the intact zone, the damaged zone, and the fault core. So the intact zone means that it's intact. Damaged zone means that you have some fractures that are usually filled with calcites, and the fault core is the zone that is the most deformed, and where you see that you have some black gouge on it. What we've done at that time is that we've been measuring the petrophysical parameters of the fault in order to see if we could find a signature of the petrophysical properties of that fault. So I show you in blue the evolution of the porosity along a borehole crossing the whole fault, and in red the density, and behind I put you in color what we've seen when we were doing the logging right after the drilling. So actually we see that we have a slight increase of porosity when we get closer to the fault core, and we see also correlated with that a decrease in the density when we go there. All of that, knowing that when we were picking our sample to do our measurements, we were always trying to be sure that we were not taking, for instance, samples with fractures in order to try to be as constant as possible during the measurement. So in Cergy, there is that apparatus that was developed that is allowing to make some P-wave velocity measurements all around the sample. So we're rotating automatically the sample of 1 degree, and so then we have an idea of the P-wave velocity all around the sample. This is a beautiful bird, or it's just the evolution of the velocity all around the sample. So you have the maximum velocity, the minimum velocity, so as a function of the angle with respect to the bedding plane. And this is a vision of the velocity all along the borehole inside of the sample. What we see is that when we go from the intact zone toward the fault core, we have a decrease of velocity and a drop when we reach the fault core. And actually, what is interesting is the fact that our petrophysical measurements seem to indicate that it's possible to assign to have a petrophysical signature of the different zones of the fault, and then and this is a marker of deformation. So first, because it reminds us of what we've seen when we've measured the velocity inside of the triaxial cell in the lab, and also that could help us to make a conceptual model of what is happening when we're forming a fault in an anisotropic material in clay-rich rocks. So you have your flat boring basin, and then at some point you start to compress it, and what is going to happen is that potentially you're going to reorientate your layers, and then at some point you're going to create in some zones some sliding areas similar to what we've observed potentially during the uniaxial deformation that with the images that I showed you with the staircase shape. Another way to go on the field is also to perform some in situ experiments. So once you've observed statically what is the petrophysical signature of what you see in the field, the idea is to go on the field as we do in the lab and try to control everything again. So this is an ongoing project. In the end, we will re-put our heaters. So let's see if maybe next year I will have some result, finally. So we've been drilling in the faults, so the same faults as before. So here in red you have the fault, and all of the lines that you see here are boreholes. There are 9 boreholes, so the 4 red lines are heating boreholes that are equipped with fiber optics and with heaters. So the design has changed slightly due to technical issues. There are some other boreholes in green here that are made to monitor with the microseismicity induced by our experiments. And so during the heating phase, we're also going to stimulate the fault thanks to an injection probe. So this is how we can decompose the whole experiment. So we're going to perform the THM stimulation in order to and we will record the temperature, the strain, and the pressure in the pressure chamber inside of the fault. And we're also monitoring seismically everything, so both passively with field acoustic sensors and actively. So this experiment, I'm going to go quickly on that. This experiment is supposed to last a bit more than 3 months because the goal is to reach 150 degrees on the field. We've been equipping the boreholes with heaters that are currently not working, but we will have new ones. This was confirmed yesterday afternoon, so great news. And those boreholes have been equipped with fiber optics in order to measure the distribution of temperature close to the fault to have an idea of temperature diffusion in the rock.
This is our injection chamber. So we're going to, so you have two packers, and in the middle we're going to inject gas because we're supposed to go above 100 degrees. So the point was to avoid to have a mix between liquid water, vapor water, and to avoid an explosion of the packer. That was initially planned. And but now the design has changed, so everything is cemented, and we also measure the temperature and the deformation in that part of the borehole. So part of the study is also to work on active seismics. So we've been performing several high resolution active seismic studies. So the first one, so this is the design of the first run of measurements, and we had a second one. So we have the receivers that are every 2 meters, and we've been shorting in between all those receivers. Now we added also an extra long borehole here in order to have a U shape, and the fault is in the middle. So we've performed a shot, like impact source. We've also done some sweep source measurements in order to see the influence of the frequency that we put on the surface, on the different resolution that we have. And we also made a borehole to borehole sweep survey as well. And this is the acoustic network. So why do we use field acoustic sensors? Because we are expecting some potential microseismicity, and so field eye sensors are the ones that are bridging the gap between what we usually do in the lab and microseismicity studies that are usually performed. And I will go to my conclusion. I think that I'm on time. So actually the point is that I've been showing you different experiments. So from the micro scale up to the 10-meter scale with those in situ experiments. Many things can be done. So at the centimeter scale also. And I will show you some perspective. The first one is, let me introduce you to Dimitri. Dimitri is a giant true TriX machine that was built in Géosciences in Nancy. So this is the machine, this is the crane to carry the sample. And so it's a true TriX, so you can apply sigma 1 and sigma 2 and sigma 3 on a sample that is roughly 1.5 by 1.5 by 1.5 meters. So that's a big sample. And the idea is to do some analogic experiments on different types of material. What I suggest is to make some experiments on polystyrene. So we started to make some tests to see how polystyrene is deforming. The good thing with polystyrene is that first, even at that size, okay, it's 50 kilos one sample, but it's still lighter than anything else, basically. So polystyrene is also able to generate acoustic emissions, so that's very good because as you probably noticed, I love to work with acoustic emission and P wave velocities, and it also has a very low. Polystyrene also has very low elastic properties, which is a very nice thing because the bigger the machine, the lower the stress you can reach. So actually Dimitri is the exact in between the centimeter scale and the in situ scale experiments. And the last thing is to try to do some fireworks, so in collaboration with the lab here, so to combine digital image correlation together with the monitoring of P wave velocity. So this is the PhD topic of Mathieu, who's there. So he's been starting to perform some experiments where he's using the camera and looking at the evolution of the velocity for now just in one direction, but the protocol has changed, so we'll probably have new results soon. And so he's been correlating his image. He's been very lucky for his first experiment. So in that case, the load is applied horizontally. As you see, he managed to generate a fracture perfectly in the center of the sample. And you see slowly over time, the time is here, his fracture propagating slowly, and actually here you have the actual deformation, and here you have the actual stress, and in blue you have the evolution of the POUYA velocities. And now he's working on how to correlate his evolution of POUYA velocities together with what he's observing directly on the images. And I will leave you on that, and thank you so much for your attention.
And the experiment is a natural example. You show a lot of veins in the damage zone. You try to identify the source of the calcite, for example, the solution cleavage or stylolite. I think I show some stylolite on your example.
So I think that Melody did that at the time.
Okay.
And me, I don't remember. I don't know if you remember, Christian, what was the origin of those veins. I'm very sorry, I'm far from being a geologist at all.
Just a question.